Okay, I divide my presentation into four sections. In first section, I will give you basic notations. In second one, I will introduce you simple homology, and in the third one, I will briefly discuss why there is at least two homologies, singular and simple one. And in the fourth section, we're going to see the exact sequences, and finally, we are going to prove the Brouwer point theorem. I gave a definition for homotopy. It's basically if I can continuously transform one of the maps into the other one, we say those maps are homotopic. And restriction is a map where if A is subset of X and Rx as an identity of A on A, we say R is retraction mapping. Okay, our first crucial definition is simplices. Formally, if n plus one points lies in at least in dimension in hyperplane dimension at least n, we say those are n simplex, and we represent it by delta n, and it can be denoted as this. And a face of a simplex is n-1 simplex if we, which is obtained by if we delete one of the vertices of the simplex, and the remaining n-1 simplex is a face of the n simplex. Here we are defining delta complex structure on a space X. Those are there are three restrictions. First one, say how nice we can do this delta simplex and simplex together. The second one tells us that if there is a sigma alpha, which is a map from delta n to delta x, then the restriction of one of the faces is also defines a map. And third one basically defines the topology of this delta complex. And we are defining a chain complex. Chain complex is a sequence of abelian groups which is connected by homomorphisms. And the crucial part is that there is a how can I say there's a here it says partial n plus 1 equals to 0. We need to have that condition, which also says that image of partial n plus 1 equals to kernel of partial n. And so image of partial n plus 1 is a subgroup of kernel of partial n. And since we defined the chain complex, we can define the homology group and homology group of the chain complex, which can be defined as this. So, because we have delta complex structure, we can define the cyclical homology of the space, and we define boundary map as this, and it is easy to check by it has some combinatoric proof. This condition also holds, so this is a chain complex. And we define cyclical homology group of of a space just as before, kernel partial n over image of partial n plus 1. And I put a little bit calculation. We can represent our torus as this. Here is the delta complex structure of torus, and we are going to calculate the torus homology groups. And with the zero simplex, only zero simplex in torus, as you can see. So delta 0 t is equals to group generated by V. Similarly, we can see the other groups as this. And we need to calculate kernel of partial n's and image of partial n plus 1s. I calculated here, and we see that kernel of partial 1 is equal to group generated by AB minus G. And image of partial 1 is 0. Similarly, we can calculate partial 2 of U equals to AB minus C, which is also equal to minus partial 2 half. Also, image of partial 2 can be found similarly. And by using those, we are going to define the homology groups of torus. Can we continue? And we see that zeroth homology group of torus is Z. The first homology group of torus is Z square. The second one is Z, and the remaining ones are 0. What does those represent? The first one tells us that the torus is path connected. The first one tells us that there is 2 types of holes. One of them is encircled by this red one, and the second copy of Z tells us that there's another type of hole, which is encircled by this blue one. And the third one, second one, tells us that there is a volume inside. We saw simple homology groups. Why do we need the simple ones? Because if we compare those, we see that the simple ones are easy to compute, and this, if we need to prove theorems, we need the singular ones. And we define singular homology group as very similarly, but this time the sigmas are not need to be nice. Like we defined 3 conditions to be structure to be a delta complex structure, but this time it is very loose. The only condition is that the sigma need to be continuous. I have given you some propositions. First one is that corresponding to the composition of a space X into path components X alpha, there's an isomorphism Hn with the direct sum alpha Hn X alpha, which tells us that we don't need to compute. We don't need to consider all groups, homology groups together. But if we divide it into path components and we compute them and we glue them together, we have the same isomorphic group. And if X is path connected and non-empty, then H of 0 of X is Z. As for any space X, H0 of X is direct sum of Z, one for each path component. And if X is a point, then Hn of X is 0. Then for n greater than 0, the H0 of X is equal to Z. We are defining the chain maps. A chain map is a map between chain groups, and those that function, that homomorphism needs to satisfy this condition. I will show. Can you please? It basically says that this diagram needs to be commutative. If we call one of these F's, those are the same things. And if there exists some Sn which satisfies these conditions for given pair of F and G, and we say F and G are chain homotopic chain maps. A chain map between chain complexes induces homomorphism between homology groups of the 2 complexes. Chain homotopic chain maps induce the same homomorphism on homology. By this 2 proposition, we can, as a corollary, we can just state our theorem right now. Which says that if 2 spaces X and Y are homotopic, then the corresponding homology groups of these 2 spaces are isomorphic. And we are ready to define the exact sequences. By using that, we'll later prove something so good. And we say that this sequence is an exact sequence if this alpha m plus image of alpha m plus 1 equals to kernel of alpha m. And we can see that it's a chain complex, because the necessary condition for being chain complex is this is subset of this, subgroup of this, and the homology groups are trivial. And here are some properties of the exact sequences. We are going to use the third one, especially in next slide. So if, okay. And why we are going to see a theorem, but first we need to investigate it's the theorem that helps us to investigate between homology group of a group and subspace of homology group of subspace of it, and by help of exact sequences we can define such exact sequence, and where I is inclusion mapping and I star is induced inclusion mapping. Similarly, J and J star is induced and quotient map and induced quotient map. And we are going to calculate homology of n sphere by using the previous theorem, and we see that if nth homology group of n sphere is Z and the remaining ones are 0. How we are going to prove it? First, we are going to take A as Sn minus 1, X as D, so X over A is Sn, and Dn is constructible, so all of its homology groups are 0. By putting A Sn minus 1 Dn and Sn into the previous theorem, we get this exact sequence, and putting zeros when we solve Dn, right there and right there, we get the this diagram, and we see that those two homology groups are equal. So because of the exact sequence property, we see that those are equal, and after that we continue our proof with induction on n. And S0 of H0 of S0 is Z, reduced homology group of S0, and the remaining parts are coming inductively. And we have a Brouwer's fixed point theorem, which states that every continuous map from Dn to Dn has a fixed point. We are going to prove it by contradiction. Okay, we are going to assume that there is some H, continuous H, which has no fixed point. Then we can define a map R such that we are starting ray from H of X to X, and we are going to define Rx as that ray intersection boundary of delta n. And we see that R is a continuous function because it's a linear combination of two continuous functions. And if X is in boundary of delta n, boundary of Dn, we said Rx is equals to X, so Rx is restriction, and we need to show no such restriction can exist. We are using the homology groups of boundary delta n, boundary Dn, and boundary and Dn. We are defining this homology group induced mappings, and we see that by first we need to define inclusion map, which is delta n, which is boundary Dn to Dn. And we see that Ri is equal to identity map. So the induced mapping R star I star needs to act as an identity mapping between the homology group of Hm minus 1 boundary Dn and Hm minus 1 boundary Dn. But we know that this group in the middle is 0 because Dn is contractible. So I star and R star cannot be identity mapping. So there is a contradiction. And I think it's the end of my presentation. I thank you everybody for listening to me. I hope you enjoyed my presentation. And if you want to ask any question, you can feel free to ask questions.
It is yours. First of all, I want to thank my mentor for the suggestion of this problem, of variance problem. And we can start. Basically, what variance problem says is if you have an integer and if you have an s, which is another positive integer, you want to be able to check the cardinality of the set of x set of s tuples such that x1 to the k plus x to the k plus xs to the k equals n, and it is easy to check that that set's cardinality is greater than 0 for some s's. If you take s greater than n, you can just take everything 1 till n, then you can take other parts 0, then you get it greater than 0. But for other s's, you need to be careful, and for the upper bound of it, the actual varying problem states that that set is bounded, and I'll try to give some bounds and estimates on that problem. And variance problem was stated by Edward Waring, which was a Cambridge mathematician in the 17th century. And the method that I'll use today was developed by Hardy and Littlewood. As you might know, G.H. Hardy was a Cambridge mathematician in the beginning of the 20th century. And before actually starting with the actual problem, we'll start with an easy version of variance problem. Easier in what sense, you might ask? Easier in a sense that we will not be concerned with the positive integers, but we'll be concerned with the negative integers as well. That way it will be easier, as you can see here. And before that, we need to define some notations. We define something called difference operator as this: delta d of f of x equals f of x plus d minus f of x. And we define the iterated different operator as a composition of different operators. And I want you to be careful about this notation because we will use it next. The delta to the power L means every single difference is 1. So iterated L times, we get this notation. And I'll make you accept these two lemmas. Their proofs are easy. Both of them depends on induction. And we'll use these lemmas to prove the easier variance problem. Easier variance problem suggests that nu k, which satisfies this equation, has which is the smallest integer satisfying this equation, is bounded above. And we can do that because if you see this is a statement, and if you try to prove it, we can take our polynomial in this lemma, in the first lemma, to be x to the k, and then we get that it is equal to this. So every number that can be written in the form k factorial times x plus m can be also written in at most k by 2 to the k minus 1 terms, because if you actually look at it, you can separate each coefficients as x minus 1, choose L many terms, and that way you get an approximate for the numbers that can be written of this form. And then in order to deal with the numbers, in order to deal with all the numbers, we use division algorithm, and then we see that we can find this, and we get that n minus r, it can be written of that form. And then in order to fix the number, in order to find the powers of x to the k such that r can be written as that, we just use one powers of 1, so that we have this form. And this is the actual statement of the variance problem. I don't want you to concern with anything on this statement for now, because we'll actually prove it later. But it's in order to understand it, this first function is bounded, and gamma function can be easily bounded, easily calculated, and this is an error term. So we can, in a sense, bound and easily estimate our function. In order to be talking about variance problem, we need to first define something called generating functions. Generating functions take in the coefficients a sequence of numbers. We are not focused on the convergence status of the power series. We're just focused on the sequence of number in the coefficients. And if we set this to be a generating function, if we set f of z to be a generating function for a set, we can calculate this f z to the power s. And in the nth coordinates, in the nth place, we get that gives us, in a sense, variance problem where we fix our set A. But for a variance problem, we are looking at the set natural numbers. And basically, how it gave the method its name was this idea in complex analysis. You might know from your complex calculus courses or complex analysis courses that if you try to integrate a function at a point, a complex function at a point where you don't know if it is differentiable or not, n times, you get this result from Cauchy's integral formula. And basically, if we write it in a series, and then we're looking at the coefficient of the nth term, we can use this. This is what Hardy a little bit did, but we will not be focused on this one. We'll use a different method that was introduced by Vinogradov. Vinogradov took a polynomial instead of the generating function, so that each of the power series, because we know that polynomials are formed in power series where the coefficients are finite. And then we can use the similar idea in polynomial and take the last power, and we can calculate that the coefficients correspond to what we expect them to be. And also I'll introduce another one. We make the change of variables, not the change of variables, but we represent complex variables with this notation for the ease of notation, because you'll see we'll have lots of these. And we define f of a, the capital F of a to the s, to capital F of a as this, and we get the capital F of a to the s is this function. And from the orthogonality relation regarding the trigonometric polynomials, we get that this set is orthonormal. So we get at every single point that this sum is not n, this n number is not the capital N. We see that it's 0. So at the point that's capital N, we get this result. And before continuing, I will introduce the big O notation. Big O notation says that f of x equals big O g of x if as x goes to infinity, if the absolute value of f of x is that there exists such m that if the absolute value of f of x is less or equal to m times g of x in absolute value for some x0, and that m does not depend on x0. So we can, in a sense, approximate this function f of x with an inside function times the constant. And I'll also use some technical lemmas. This is a Dirichlet's theorem or lemma, whatever you call it. And it says that for every alpha and cube positive, cube greater than 1, we get this result. We get that there is a rational number such that this is satisfied. This is a result using the Fontaine approximation quite a lot. And this is the Wales inequality. Now it's not the time to deal with it because it looks complex. It is complex, but we'll use it in a specific point that it will make our jobs easier. And it's the same thing with Hual's lemma. And first, we need to construct, in order to estimate this integral, we need to divide it into two parts, where we'll call the first one major arcs, second one minor arcs. Major arcs will be important in a sense that they will be the estimate for our integral. Minor arcs will be negligible compared to the major arcs. We construct major arcs is this. This set is called the union of the major arcs, and we pick nu as less than 1/5 because of the reason that you'll see later. And we take minor arcs to be the complements of major arcs in the 0-1 interval. And then we get our first result, where when I say minor arcs, I mean 0-1 minus major arcs. Remember that. And we can bound it with this function. Remember, p was defined as that. P is the floor function of n to the power 1/k. And in order to prove that, we need to use Dirichlet's theorem, and we pick in Dirichlet's theorem q as p to the k minus nu. And then we use other results. These are we try to fix Q, and then we look at where Q can take its places if alpha is in minor arcs. And then we see that Q needs to be in between P to the nu minus P to the nu and P to the K minus nu, because in other cases, we'll see that it falls into a major arc, which is not the case because it's the complement of the other one. And then we use the Wales inequality here to bound this function, and then instead of n, remember we had n there, we take p, and then we get this bond on this one. Important part to notice here is that this notation means that there is a constant depending on k and epsilon, such that the f of alpha is less than that constant times this value. And then we use Hual's lemma after this step. We just use we just add and subtract f of alpha to the power 2 to the t, and then we use ML argumentation to just bound it above, and then we use Hual's lemma to bound this function, and this one is also already bounded. So through that we get our result. And then for the major arcs, we dealt with minor arcs. For the major arcs, we assume these lemmas. We'll use them later, and this notation will be introduced. And yes, this is another theorem. In the proof of this theorem, we'll use the lemmas that I just mentioned, and then this integral we'll also deal with it later. To see that it can be formed into a better one, in a sense that it will be evaluatable. And we see where we take news less than 105 to ensure that this is greater than 0, because we'll use these deltas in this, as you might have remembered from the statement of actual theorem. And then we need to bound it with this. In order to do it, we will just use some evaluation. But it is important to notice that, like, we are trying, in order for us to bond it, we'll use the lemma 1 here, and lemma 1 here to bond v from upper with a p, and we also use the lemma 2 to bond this function. That those two lemmas will be utilized here to get our actual bond. And then we also know from the calculation that the measure of this union of these sets, since these are half intervals, these are like, we are looking at 0-1 closed interval, these correspond to half of them. So their measure equals to length, and it should be 2 to the p to the nu minus k for the intervals like these. And then we'll have the measure of every single other one equals 2 to p to the nu minus k again. And then in order to get the whole measure, we need to add them up, because these are disjoint unions of major arcs. We can easily prove that through the relation. And in order to add them up, we need to have this phi function is the Euler's phi function, which counts the number of numbers less than q such that they're relatively prime to q. And through the use of that, we can actually bound it as such. And after that, we can actually, it's easy to see that this is bounded above by this value. And if we combine our results, remember in this one, we found that it was p to the s minus 1 plus 2 nu. If you combine it with this bound, we get that our function, our integral is bounded above by this value, p to the s minus k minus delta 2, such that delta 2 is of this form. And then we can write our function as of this form. And after that, we continue to evaluate our function, because we want to be able to get the j star integral part, remember? And then these are just evaluation tricks. We just separate them and we evaluate each one of them, and then we put them together. And remember, like, we are focusing on the major arcs themselves individually. These are the bounds on the major arcs. These for every single rational number in the 0-1 interval. And as I said, we are separating them and we are putting them together. And then we get our result. This was the integral that was defined before. And when we combine them, we get that, like, after change of variables, we get our integral, you see. And then after we combine everything, we get our result. And we define something called the singular integral for variance problem. This singular integral is a tool from harmonic analysis. We define it so that it helps us actually. You see, it is kind of similar to the function that we defined here. It's kind of similar to this one. We generalize that. And then to evaluate that integral, we need to have some, we need to bound this integral so that we can get our actual result. In order to bound this integral, we have this theorem that says there exists a bound. I will not go really deep into this proof of this theorem, but basically it divides the interval into two again. And then from the one side, the minimum value is different. From the other side, minimum value is different. And it evaluates the integral for those two sides. And then it combines the result to get this bound. And then it's easy to see that this is also a result of it, because this J star was found in the previous theorem. And then in the end, we get this result. And now we are simply coming to the end. It's not the end, but it is really closer. As you can see, we can bound Jn as a function depending on a gamma function and with an array term of n to the s minus 1 over k plus minus 1. We define also a singular series. Well, what is called a singular series is this series. This was somewhat similar to the one that we've seen earlier in the Theorem 3. And we used this singular series in our statement of the range problem again. Our lemma is that this is a uniformly convergent. Actually, it's easier to see this result because if we take such epsilon, then we can do some algebraic manipulation to get this result, where this is easy to see again. And then if we fix delta 4 as this one, then we get our every single term in our function is bounded by 1 over q to the 1 plus delta 4, and delta 4 is positive. So we get that this series is bounded and like it is convergent, and also it is uniformly convergent. So it is actually uniformly bounded. And then our last theorem is this one. It says that the series that I just defined, this one, which depend on this notation, is actually bounded above by a constant and below by a constant depending on k on s. And we can actually get this result through use of elementary number theoretical methods, but I will not go deep into that result. And it also tells us that this function separately, this was the finite part of the series. The finite part is really close to the actual series in a sense that it's got this error term. And now we are able to prove the actual statement of our theorem. Let's go back to the theorem first. Sorry, I missed it. Yeah, this was our statement, remember? And we had to, you see, this was kind of similar to our Jn. This was actually our Jn bond. And this was a series that we defined. And this is the bond that we found earlier. And this is the last theorem. And we'll now combine all of this information. And in order to do that, we fixed some delta. And we separate our integral as we started in major arcs and minor arcs. For major arcs contribution, we get this result from our theorems. And for minor arcs contribution, we get this bond from our theorems again. And then we further separated into these two forms. We calculated this in the Theorem 4 and this one in Theorem 2. And also the bonds are found there as well. And then we multiply them. We get this result in the middle and in the part below. And then after which we can just use the estimate that we found on Jn to conclude our proof in two steps. First this one, and then to write it neatly, we let delta equals delta 0 over k, and then we get our result. And thanks for your attention.
Okay, this is the outline. So first we are going to talk about what is the cable equation is, and we try to derive it and then solve it numerically, and we will check the stability and the other properties. So this is the passive cable equation, which is a fundamental model in neuroscience. So it describes the voltage distribution along the dendrite, which is a part of the neuron. And as you can see, it is our equation is linear with constant coefficient, and parabolic equation, parabolic partial differential equation, and with the time and space constants. Before starting the derivation, we need some biological background, very little. Since we are trying to model the signal propagation along the dendrites, let's look at them. So they are basically the receiving signal receiving units in the neuron, and they are covered by a biological surface, which is called membrane. And on that membrane, there are like little doors, which is called ion channels, which helps to ion to transfer in and out. And so for the derivation, we will use the cylindrical compartment method, compartmental model. Figure 1 shows a microscopic image of a segment of a dendrite, and our derivation is based on dividing this dendrite into a cylindrical compartment, as illustrated in figure 2. But we need to quickly define the parameters. So first one is we have a current flowing inside the cylinder, and this current can go to the membrane also. So we have a membrane current, which consists of 2 parts. First part goes to the membrane in itself to charge the membrane surface. And the second one is flows from the ion channels. And we have a delta X, which is the compartmental length, and L is the length of the cylinder. And also we need to define voltage, which is, these 3 are important. Longitudinal resistance, which is basically the resistance along the dendrite. And we have a membrane resistance because of the ion channels. And we have a membrane capacitance because of the membrane surface in itself. Yes. Oh, and they defined by per unit length. This is important for the next slide. So we will select a non-boundary compartment, as you can see in figure 3, and we will just apply the Ohm's law on it. And the important part here is to identify the resistance along the compartment. So we just multiply longitudinal resistance by the compartmental length, because this is per unit length, and the negative sign because of the passive sign convention, and it indicates the voltage is decreasing. So after we apply Ohm's law, we get our first partial equation. This will be helpful for deriving the cable equation. Let's try to remember that. And after that, we apply Kirchhoff's law to a compartment. But in order to apply Kirchhoff's law, we need a junction point, and we need to identify the entering and leaving currents. So as you can see in figure 3, we will think the compartment as a junction point, and we have a current at position X is entering and other one is leaving. So when we write it as this equation, left-hand side entering currents, right-hand side leaving currents, and when we solve this for a membrane current, and as the compartmental length goes to 0, we have the second useful equation. This is also be useful for the derivation part. And we need to now find the membrane current to give a meaning of this equation. So now we will model the membrane surface as a circuit. So this is the inside of the cell. This is the surface of the membrane. A capacitance show the membrane itself. Current charges the membrane, so we use a capacitance, and also resistance represents the ion channels. And above of this circuit is the outside of the cell. So we will again use the Kirchhoff's law at the above junction point at here, and then we get the membrane current in terms of the resistance and the capacitance currents. Now we have to find them. We just find them by, for example, capacitance current by the capacitance equation, and resistance current by just simply applying again Ohm's law, because we know the resistance and capacitance. Now, if we substitute them, now we can find the membrane current in terms of only voltage. This is important because we try to find an equation only in terms of voltage. And if you remember, we found this first equation from the Kirchhoff's law, and from a second equation from the Ohm's law. Now the problem is we need to find a formula only in terms of voltage by using these 3 equations. So the first observation is directly we can substitute the membrane current into the first equation. So after that, we have this first equation. Now we have to identify the left-hand side, and we will use it, the second equation, which comes from the Ohm's law. If we take the partial derivative of with respect to x, we just simplifies the di dx. So now we have a common term. After we substitute the first equation into the second one, we get our cable equation. Actually, this is not the cable equation, but we found only in terms of the voltage. Okay, after defining some constants and space and time constants, we will deal with this initial boundary value problem. So the constant A is positive and B is negative. This is important for the stability part. And we will use for the boundary conditions constant voltages, which is called the voltage Clement model. Now, in order to solve to solve our equation numerically, we need to discretize our domain. So this is a standard procedure. So we need just delta x and delta t in here. We need to define delta x and delta t in here. And we will denote our solution at the position xi and tj by the vi and j. So, okay, first we will apply the explicit method. So in this method, our goal is to compute the next time step. If I can show you. The next time step j plus 1 by using the current time steps at the time j. So for the time derivative, we will just use the forward difference formula, and for the second order spatial derivative, we will use the central difference formula. After substituting all of them, we get our finite difference equation. Finite difference equation. Again, let's observe that constant A is positive and B is negative, and R is in terms of the step sizes. And other method is Crank-Nicolson implicit method. So it has a very basic idea. It just assumes that the partial differential equation is satisfied at the midpoint of j and j plus 1. And we will use again the central difference in time and space. So after substituting our approximations, we have again a finite difference equation. Now in this equation, we have a constant A positive and B also is positive. And now we will investigate the stability. So the idea of stability is actually very simple. We apply a numerical method, and we want to ensure that this numerical method does not amplify the error, does not cause error to grow. And with the initial conditions, we try to limit the amplification of all components of it. So now assume that we have a partial differential equation, which is linear with constant coefficients, which is our table equations one of the properties, and with periodic initial data of period. And we have an approximation 2-time level. This means we have used current and next time step. Now the definition of the stability, according to Lax-Richtmeier definition, we want to solution to remain bounded as the time steps goes to 0. So we want the solution to remain bounded as the time steps goes to 0. And the von Neumann stability condition tells us the numerical scheme is stable if amplification factor is less than or equal to 1. So how to derive this inequality? Our approach will be like this. We will first write the initial conditions in terms of exponential form of Fourier series. And second, we will use separation of variables to split the solution. And after that, we will investigate this function with the stability definition. So it is a very great idea. And now we write in this slide, in this particular slide, we write the initial value in terms of the exponential form of the Fourier series, and we reach this sum. So we have a constant and some e terms. Let's see them more clearly because it's hard to explain in that form. So for various p's, we have initial values. We can write initial values in terms of like this, a constant and e term. And since we are dealing with the linear equations, we can pick any initial value and we can check its one of the components to analyze its propagation. Yes, this propagation. So for example, we can choose this initial value and we will look at this component of it. And we will neglect the constant terms. Now we apply the separation of variable to our solution. So we write it in terms of x and t, and we will define the amplification factor is e to the power some constant and the time step. And also now we will connect with the stability definition, which says that we need to bound solution. So we take the just absolute value of it in this form. And from the Euler's identity, this right part is 1, and we resulted it in the amplification factor power to q. So in order to remain solution to be bounded, you can easily see that the amplification factor must be less than or equal to 1. So now we construct our methods. Now we just apply for our numerical schemes. So first one is explicit method. So the explicit finite difference equation approximates the cable equation at the P and Q points. So now we just substitute the term we founded earlier, and after simplifying, we get the amplification factor, this term. So now by triangular inequality, we can say that amplification factor is less than some absolute value term minus b times time step. And now b becomes positive in this step. And now our goal is to show that this is equal to less than or equal to 1. So it's enough to show that the absolute value term is less than or equal to 1. And after solve this inequality, we get our stability condition. So it is not always stable. It depends on some condition, which is important. But in the Craig-Nicholson scheme, we see it differently. We saw something different. When we again apply this method to the Craig-Nicholson, and after simplification, we find the amplification factor is absolute values of this messy term, but these terms are same. And because of this term positive, we can easily show that it's less than or equal to 1. Also, you can show it by contradiction method. So because it's less than or equal to 1, we directly say it is unconditionally stable. So it do not have any condition, doesn't require any condition. So now we give the Lex equivalence theorem, which connects the ideas of stability, consistency, and convergency. And we will see the consistency part in the next slide. But the Lex equivalence theorem says that if we have a well-posed linear initial value problem and linear finite difference approximation, so if we can show the stability and the consistency part, we don't need to check the convergence part. Or from the other direction, if we show the convergence, we can do not check the stability and consistency part. The scheme is stable and consistent. Okay, now we will try to apply this theorem. And in order to apply this theorem, remember we have shown the stability of the explicit theorem. We have shown the stability of the explicit method. And now if we can show the consistency part, now we can say that it is convergence. So in order to define the consistency, we need to first define the truncation error, and which is the basically so if we have a solution to our partial differential equation, it is the exact solution, and if we put it into our difference equation, this will be our local truncation error, which is intuitively means that how it measures how much our numerical scheme misses the real solutions. And we will define the consistency as this local truncation error goes to 0 as the time steps goes to 0. If it goes to 0 as time steps goes to 0, it is consistent. And again, we apply it to the explicit scheme. So let big V be the exact solution of the cable equation. So remember, we have obtained our finite difference equation. We just substitute the exact solution to it. And K and H represents the time steps in here. So now we can write this. We can write insight by using the Taylor's expansion. Again, a very simple idea. We just use the Taylor expansion for to get truncation error. And after writing by using Taylor expansion, we get this first equation. And please observe that the first parenthesis term, is nothing but our cable equation. So cable equation. So it's equal to 0. And after that, we left with only these terms. So after this is 0, we left only with these terms. And these terms in terms of K and H, which is the time step and space step. So one can easily show that this goes to 0 as this time steps goes to 0. And because of that, our explicit difference scheme is consistent. Now we reach the conclusion. So far, we drive the cable equation. We drive our cable equation, and we try to solve it numerically, and we check their stabilities. And we see that for the explicit part, we have a conditional stability. Conditional stability, and the Crank-Nicholson is the unconditional stable. So, and after we apply the Lax equivalence theorem, and we state that it is our explicit difference equation is a convergence because it is stable and consistent. And we established the von Neumann stability method. So this is my references. I hope you enjoyed the presentation. Thank you very much for listening to me.
Hello everyone. I start with thank my mentor because she's very helpful to me, and we're gonna cover some examples in group theory, which one has some surprisingly, intuitively unexpected results. And I kindly encourage you to participate my slides via raising your hands when I ask if this statement is true or not. Okay, before giving some statements, I really refresh your memories. First one is definition of group theory, group structure. Group structure is a structure that if we have a set and if we define a binary operation, this structure respects 3 axioms. First one is associativity, probably most of them primitively. Second one is identity property, also. And lastly, inverse of every element in G. And the other fundamental definition is subgroup. If H is a subset of G, and if this H is has a group structure under the same operation with G, then we call it subgroup of G. Okay, there's some really basic examples of groups and non-examples. Probably you're familiar with these also. And before give the first statement, there's another basic definition. We say that group G is abelian if any element in G can commute with each other with respect to this equation. So our first statement says that every group whose proper subgroups are abelian is also abelian. What do you think? Anyone can, okay, probably most of you, this is a false statement, right? Let's see. Yes, it turns out to be false. We can we can consider symmetric group S3 as a counterexample, and all subgroups are abelian, but itself is not, since any transpositions, multiplication of transposition gives different results. Okay, the second statement is familiar with the first one as a structure. Before that, there is another basic definition. If n subgroup n is normal, if satisfying this equation for all G, and we can say G is a cyclic group if it can be created, it's one element, and we can denote as this notation. Lastly, we can define index without introducing cosets, like quotient of their orders, numbers of orders. And second statement says that every group whose subgroups are all normal, then they are abelian. Is it true? You can raise hands if you think is it true, or is it false? Is there anyone? Okay. Let's see. It's also false, since we can take counterexample as quaternion groups QA, and subgroups are all in this form, which are the generators of Q8. Subgroups of Q8 are abelian, but itself is not. We know that, and also we know that all subgroups are normal in Q8, since the generators are IJK has index 2, and okay, I actually check, because 1 and -1 is random. And there's another definition. If we have a group G, we can say that group G finitely generated group if it has some finite set S, so that the element of G can be written as in this set as a combination of finite many multiples of that. So our third statement states that there exist groups that are not finite. You agree with this statement? You can raise hands if you agree. Okay, let's see. It's turned out to be true, because we can introduce a claim to prove. Claim says that every group of rationals is not finitely generated, and proof is long, but just algebraic manipulation. So I wrote here a sketch of the proof. Suppose that irrationals is generated by finitely many rationals Q1 through Qn, and let integer d is the least common denominator of these rationals. But if we consider 1 over d plus 1 in rationals, it cannot be generated whole set of rational numbers. Therefore, the statement is true. Okay, there is more definitions. First definition is about automorphisms. A map of phi is a automorphism if there exists an isomorphism from G to itself. And we call automorphism group of G if all automorphisms of G under group operation, which is function composition, then we denote by all G. There is another basic example here. And let's see our fourth statement. The exists group satisfying automorphisms of G is isomorphic to G. Do you agree? Okay, let's see. Yes, this turns out to be true. We can consider symmetric group S3 with this phi map, which sends G to conjugation by and sigma. G and sigma are elements of S3. And I wrote all the conjugations of this map, and let another map, which from S3 to automorphisms of S3, it's satisfying that psi of G equals to phi sigma. Then we can, if we can show this psi is isomorphism, then we are done. Since this is a bijective map, we are okay with the bijective property, and we just show the homomorphism part. With these algebraic manipulations, it's true that homomorphism property holds. Then this is the isomorphism. Then yes, automorphism of G, isomorphic to G. Okay, let's proceed. There is another definitions. Person is characteristic subgroup. A subgroup H of G is called characteristic if there is a, for all the phi's, which are automorphisms of G, satisfying that maps H to itself. Okay? And center of G is defined as elements in G, which commute with all other elements in G. Okay. Then our fifth example says that actually center of G is center of G is a characteristic. Okay. What do you think about it?
Oh,
True. Let's see. Yes, it is turned out to be true. And if we just show that image under alpha of center of G, inclusion of center of G, then we are done because alpha inverse is another automorphism since this is bijective. To start the proof, let's take X in the image of center G on alpha, and we can show that there is a Y in center of G with alpha of Y equals X. We can take any G and we can claim that this G equals some element in G as a alpha of G prime. Okay, then Xg equals alpha of Y times alpha of G prime. We can glue them because this is a whole automorphism. Then we can club because Y is in the center. Then also we can separate again, and we can write down as a Gx, which says that for all G, Xg equals Gx, if X in the center of G. Therefore, yes, this map is an automorphism. This map is true for all automorphisms of G. Okay. Let's continue. Our sixth statement in this time says that if n normal is in G, is it possible that this alpha of n is a characteristic? What do you think about it? Good. Is there anyone? Good. False? Sam? You don't know. Some of them you don't know. Okay. This turned out to be false. As an example, take G as a Klein-Fork group, which can be represented as Z2 cross Z2. And this group is abelian, we know that. This And since this group is abelian, all subgroups are normal. And let's choose a normal subgroup of B4 generated by 1, 0. Their elements are 0, 0 and 1, 0. And let's consider an automorphism of B4, which swaps first element to the second one and second one to the first one. Okay. Then we can show that image of n on alpha is 0, 0 and 0, 1, which can be represented as this. And we claim that we know that they are not equal, since generators are not equal. Okay. If two finite groups have the same order profile, then the groups are isomorphic. Maybe I recall that what is the same order profile. It's if two groups has there's nothing about this. Okay, I can tell this as it's. If two groups have same order profile, then their elements distributed in the same way as orders. Now, okay. No. Let's what's the answer is false. And if we look at the counter example, maybe you understand what is order profile is. Let's take G as a quaternion group close to Z2 and H as Z4 cross Z4. We know that both groups have order 16 and their elements order are distributed identically, which means that same order profile. One element of order 2, 3 elements of order 2, and etc. Then we know that G is non-abelian since quaternion group is, while H is abelian, then they cannot be isomorphic. Although they have same order profile. Okay. Second, eighth statement says that if M and N are normal subgroups of G, such that quotient groups are isomorphic with G, then M isomorphic to N. What do you think about this? True? Okay. This turned out to be false. As a counterexample, let's take G as Z2 cross Z4 and M as some generator that isomorphic to Z4, and take another generator which generated by two elements, which isomorphic to Z2 cross Z2. And if we do some basic calculations, we claim that G quotient M isomorphic to Z and G quotient M. But M and N are not isomorphic, since Z4 and Z2 cross Z2 is not isomorphic to each other. Okay, this is our last example, but it has some parts. Before that, let's recall Lagrange theorem. All of them, I guess, heard this at least once. Okay, first part of the last question, the last statement is that group of order P and P squared are abelian, where P is a prime. What do you think about this? Is it true? Or maybe one can say it is true for P, or it is not true for squared. Okay, almost everybody said it is true. It's turned out to be indeed true. For P part, let order of G as P, and we know that P is a prime number, so it is greater or equal than 2, we know that. Then there is at least one G in group G that is not identity element. By Lagrange theorem, the order of any element must divide P, we know that. since G is not identity, and it should be divided order of G, then the only possibility is P for the G. Okay, then we claim that G has order P, and we know that our group also has order P. Then it's a cyclic group generated by G, and all cyclic groups are available. Therefore, P part is true. Okay, there is some definition. A group whose order is power of a prime is called a P group, and there are two theorems. First one says that non-trivial P group has non-trivial center, which says that order of the center greater than 1. The second is one says that quotient group with quotient center of G is cyclic, then G must be available. Okay. For the P square part, this is a P group, we know that, and theorem 1 says that center of G cannot be, order of center of G cannot be 1. Then order of center, there is two possibilities, P and P square. If order of center is P square, then center equals to group itself, so G is invariant. But this is literally little long proof, and this is just a sketch, the second part. If order of center G equals to P, then order of the quotient also equals P. Therefore, G quotient center is cyclic. And let's go to theorem 2. If quotient group with quotient center of G is cyclic, then G must be abelian. It turns out to be abelian, but there is some contradiction statement here. Maybe we can argue that later. Okay, this is the last question. And group of order PQ and PQ are abelian, where P and Q are primes, and P less than Q. False, right? Okay. Yes, both of them for it is false. For the PQ, we can consider quaternion group, it's obvious. And for the PQ part, consider the symmetric group 3. We can set P as 2 and Q as 3. Then it is also a abelian group. Okay, these are my all statements in this presentation. Our examples from Bergman and definitions and theorems from abstract algebra from Dicle. Thank you very much for
Thank you. So I will be starting with the introduction on algebraic coding theory, and I will be just giving more of a definition so that it will be a base for the cryptography, and then my friend Bahar will give an introduction on applications on cryptography. So our first definition is the linear code. A linear code, let's say C, is it's just a subspace of a finite field FQ. Q is a prime number here, and it's denoted as nk. So it's length n and dimension k. So another definition is a Hamming weight. A Hamming weight of a vector of a finite field is defined as the number of the non-zero elements of it. So if you wanted to give an example, let's say that C here is a finite field, it's closed under the operations of the FQ. So it's length 4, and we also find the length of it as a Q to the K. It's just a fact. I'm not going to explain it. So the first element vector of C is a 0 vector, so we have the weight of C as 5. It's a 5 length also. So, and the last one is a 1, 1, 0, 0, 0 vector, so it has 3 0 components, so we say that its weight, Hamming weight is 3. So then we can define Hamming distance. Now we take two vectors from a finite field and we check the non-equal components, but they have to be the same index, of course. And the number of non-equal components is the distance. So for a linear code, we can induce Hamming distance from Hamming weight as this. This is certain for linear codes, as a linear code is a subspace, and we are certainly know that x minus y isn't also C again. So minimum distance is just the minimum distance of the whole vectors of C. And in the first example, C1 was our 0 vector and C2 was 1, 0, 0, 0. So we have one non-equal component. That's why the distance is 1. And after checking all the distances, we know that this minimum distance of C is equals to 1. So a decoding algorithm is mostly used in cryptography. So I will just give an example, the definition, and my friend will give an application of it. So the code block of errors has an error correcting capacity. We usually denote it with T. And if the minimum distance of C is up to T, then we say that the error capacity of C is T. And a decoding algorithm defines the closest code word Y in C for a given X in the neighborhood of Y with a distance of T. And we can also restrict it, this minimum distance with singleton bound. So we have a linear code C with length n and dimension k, and we say that the h is less or equal than n minus k plus 1. We can prove this theorem with defining a map that deletes the last the h minus 1 components of C, and we can show that this is injective, and then we can use the cardinality of the sets, and then show that this equation inequality works. We can also have generator matrices for the linear codes. So we obtain C from G. So the columns of G gives a basis for, the rows of G gives a basis for C. So we can obtain the elements of C from the generator matrix. This is an example for the first linear code we gave. And a parity check matrix is the rows of H when we made the basic matrix multiplication with the rows of C, rows of H, and the transpose of the elements of the linear code, we have the parity check matrix. And we say XH transpose is a syndrome for any X. This parity check matrix is used in the also error correction definitions. So we can finally begin some family of codes. Reed-Solomon code is a evaluation of some polynomials. So we just choose a polynomial from the finite field with degree less than k, and here alpha is an n-tuple of distinct elements and beta is an n-tuple of non-zero elements. So we just obtain the generalized Reed-Solomon codes like this. And if we choose B beta as 1, then we have a Reed-Solomon code. So this is an example of a Reed-Solomon code. We choose alpha input as this and let f be an x plus 1. Then just doing the calculations, we have a code. Now, classical GOPA codes. GOPA codes are the first algebraic codes introduced, and they are used in the Macaulay's framework, which is a framework in the cryptography. So we define a quotient ring first. Here, we choose a G polynomial G in the final field and define the quotient ring. Then the classical GOPA code is the basic where the reminders of a division are 0 in mod Sm. So it's a little bit of a long example, but it makes sense when it makes sense in the end. So we choose parameters. We want to define a GOPA code 332. So we define the final field as n to the q to the 3 to the 2 to the 3 and f8. F8 is isomorphic to this field, so we just choose a polynomial. And we choose alpha as the root of this. So we have f8 with these elements, and then we choose another irreducible polynomial in f8. So this is our GOPA polynomial. Then we construct the quotient ring S3 as this. So we want to await the roots in G, so it's not 0. And we choose the support set. This is because we don't want the roots of G as 1 alpha to the 2 alpha to the 2 plus 1. And we construct the parity check matrix over F2. We did all before this in F8, but now we are in F2. So we obtain this as a parity check matrix. And we can expand this to, so Macaulay's usually first used a binary GOPA code. So we want to expand it to F2 using a 3-bit column vector. This gives 1, just 1, 0, 0 gives 1, and 1, 1, 0 gives alpha, 1 plus alpha. So we just expand it like this. So the rank of the parity check matrix here is 2, and we had the length of the GOPA code as 3, and we have the dimension of the GOPA code 1. So we only have the trivial code, which is just 0, 0, 0. If you want a non-trivial code, then we have to choose n bigger. So a cyclic code, we define a cyclic code over a cyclic shift. So if all the shifts of the linear code C is also again is C, then this is a cyclic code. Like our first example, it was not a cyclic code because one of the cyclic shifts is not in C, but all the cyclic shifts of this C is in the C, so we can say that it's a cyclic code. Now we have a Reed-Muller code. So this is also obtained from an evaluation of polynomials. So we define the map called evaluation map, and there is a vector space polynomial we defined, and so it's just the evaluation of polynomials again. And here R is important because here R is determine the error correction of the Reed-Muller codes. So lastly, we have code equivalence. Here the most important part of the code equivalence is permutation equivalence. We have, if there is a permutation of indices that turns C1 into C2. So for example, if you want to check if these two matrices are permutation equivalent and we are generator matrices are given, we can find C's from the generator matrices, and we also know the finite fields they are defined over. So we cannot find any permutation that turns C1 into C2, so we can just say that they are not permutation equivalent. But there is a more important proposition for this. So we can, if we have two permutation equivalent codes, then we can say that their generator matrices are connected by this equality. So here S is a invertible matrix and P is an n by n permutation matrix. So we can prove this by saying that, like, if they are permutation equivalent, then we can say that T2 is generated by the permutation of the generator matrix of C1. Then we can also use another base for the generator of G2 to obtain C2, and so that we can find an invertible matrix and we can obtain this equality in the end. And we can also solve the example before with this. So let's just choose a permutation 1, 2, and express it with its representation matrix. So we have G1P as this, but we cannot find any invertible matrix with satisfying these equations. Thus, there is no such S exist. And if you want to repeat the same process for the all permutation matrices, we obtain no solution. So this was the end of my presentation. Thank you for listening.
Hi everyone. Today I'm going to talk about coding theory, cryptography based on coding theory. Before I start, I want to give you a kind of introduction about cryptography. Basically, in cryptography, we have two people called, very famously, Alice and Bob. They all want to send message. They want to talk to each other. And then they have Eve, who listen to them. We want Eve don't understand anything about Alice and Bob, what we were talking about. So Alice has message M, it's turned into C, and all Eve C on the channel is C. We want Eve don't understand anything particular about C. Not even like how word it is, how many like phrases it has, nothing. So we have some special techniques. First, the protocol is public key encryption. Public key encryption is basically arithmetic cryptography used per pair of keys. A public key for encryption and secret key for decryption. You may think that how it may work. First, I have to say that just think about your Gmail address or email address. You have a username and password. Everyone knows your email address, so it's your public key. When someone sends you a message, it's encrypted with your email address. And when you open that your actually box with your password, you decrypt it with your password. So your password is your secret key. And in this algorithm, in this protocol, we have a key generation, which create a public key for us and secret key. And it must be computationally feasible to find a secret key S or message M from public key P and cipher text C, because the only thing Eve knows is C and P, nothing else. So we should know nothing or understand anything about S or M. You may think how they doing it. Actually, they use some sort of hard mathematical problems. One of them is one of the most famous one called the RSA algorithm. So I'm going to say how it goes. First, you choose two big prime numbers. You compute their module like n, and then you compute phi n. And it's going to be p minus 1 in q minus 1. And then you choose like a public exponent such that GCD gonna be 1 with phi n. And then your public key gonna be N and E, and secret key contains P and Q and D. And D is basically inverse of E to mod phi n. Now I want to look at this encryption method. It's basically multiple M with E, power with E, and then compute its mode to N, and it receives C. It sends C to like Bob, and for Bob decrypted, it's used its own secret key, and compute D. Then from D, it's compute N. After that, I'm gonna talk about one of the important cryptography tools called hash function. A hash function is basically take anything you gave it, like any size, and take it to a fixed size. No matter how big or how small it is, it's take it, and for example, it's gonna be 64 bytes. And it's important because you can generate like secure key derivation, digital signatures, and data integrity. And it has to be deterministic. It means each time you give it the same input, it has to generate the same output. And it has to be collision resistant. It means it has to be hard to find two inputs which produce same output. And it should be one way, meaning it should be easy to give it input and calculate output. But when you see the output, it should be hard to kind of reverse it and calculate the input. And you can see my example here. One of the hash function is SHA 256, which maps everything to 256 bits. And now I want to talk about some practical application of hash function. One of them, as I said, like a key encapsulation mechanism. But it's a very interesting like application because when you're working with public keys, it's a quite hard, or better say, it uses memory and space. So we are always looking for easier way and faster ways. Symmetric encryption, like secret key encryption, are mostly used because they are easier. But there is a problem about secret key that you have to come to a place with the one you want to talk about secretly and share a secret key with them. But you can solve it here by, you choose a random M, you encrypt it with their public key, send it to them, and you both now have M. You use a hash function, generate a hash of that M. Now you have a big M, and from now on, you use big M as your secret key, both for communication. And one other of their application is digital signature, which is provides authentication and integrity. The key roles are like signed with the secret key. For example, a signature is like your sign at the end of the letter. When you send a letter to someone, you sign it with your signature. And if in the future someone finds that letter, you cannot say it wasn't me because they can see your signature in the end. And this is happened by S here. S is your secret key, and only one who has it is you. So when you sign it with your secret key, in future you cannot say that it wasn't me, because only you had your secret key, and they can verify it with your public key here. Now I want to talk more about public, like coding theory and application in cryptography, and overview of code-based public key frameworks. The core idea is based security on hardness of decoding a random linear code. It means NP hard problems. As you see, RSA was a hard problem to solve. We use two big prime numbers, and here we are going to use the hardness of decoding random linear, as my friend explained earlier. We have a private key, a linear code C with efficient decoding, and we also have public key. This guy is the version of C' that appears random. Encryption encode message as a corrupted code word, and decryption use secret code to decode. And I'm gonna introduce Maclist and Niederreiter. Maclist is discuss the generator matrix, and Niederreiter discuss parity check matrix, which my friend explained. Now let's talk about Maclist. It's basically an space code C over a Q with the decoding up to T errors. It means like it can decode it if it had just only the T errors or less. If it's gonna be more, it can't work. Generator matrix G of C, and it's a scramble G prime, and it's produced SGP, and your public key gonna be from now on this T and like G prime, and your private key gonna be G and S and P. Again, I have to mention that this is hard to compute the like private key from like your public key. And you have message M with error in this space with the weight, Hamming weight smaller than T. Then you'll create your ciphertext. And for decryption, Alice gonna like use this because it has her own secret key and decoded like this. This is an example. I have 7-4 space binary Hamming code with T1 generated matrix, this matrix and S and specific P public G prime. My M gonna be this, and then my error gonna be this, and I calculate C like this as I shown here, and then I have for decryption I use a CP inverse, and I generate this decoded, and I can recover it.
I want to start my presentation with J.D.H. Smith's verse about universal algebra, and he says that what looks messy and complicated in a particular framework may turn out to be simple and obvious in the proper general way. And it will be our main motivation of the presentation. Firstly, we will introduce you some basic elements of universal algebra. Then we will talk about Birkhoff's variety theorem. And what is universal algebra? Universal algebra is a mathematical structure that studies about algebraic structure with focusing on sets with operations and identities that satisfy. Also, universal algebra abstract algebraic structures and ask that what properties they share with each other and how they relate. And with that, we can say that the aim of universal algebra is revealing some common facts and simplifying proofs without checking everything, every algebraic structure separately. Now, syntax refers to the rules that define how symbols and equations are correct structures, while semantic means that what that sentence means and how that equations are related to mathematical concepts. And we will make a bridge between them while we check the Birkhoff's variety theorem. And before starting that, I think we should read what is Birkhoff's variety theorem. It says that K is an equation class if and only if K is a variety, but we will see that in the end of the presentation. Firstly, I think we should start the definition with algebra because everything about algebra. If let A is a non-empty set and F is also the function, family of functions, operations on A, and algebra A is the pair of A and F. Also, and some of the simple or maybe most common examples for algebra is group centrics. If an relation d'équivalence theta satisfies the compatibility property, then we say that theta is a congruence. And what is a compatibility property? it's for all the elements in A. If theta satisfy A, theta B, and the image of A, theta image of B also, we say that this is the compatibility property. And all the congruence on A denoted by con A. Also, we can define normal subgroups as congruence in groups, and ideals as congruence for the rings also. If class of algebra K close under isomorphism, homomorphism, subalgebra and direct product, we say that K is a variety, and V of K is denoted by the smallest variety containing K and also generated by K. And while groups are an example for variety, we can say that fields are also a variety because fields are not closed under direct products. Let X a set of distinct objects and we call them variables. And if we want to find the terms of X, we say that if T of X includes, term of X includes that elements of X, also polynomials of that elements, and also that polynomials under that operations are also terms of X. And if we say that set of X includes A, B, and C, and our operations are, for example, product addition and multiplication, and some of our terms are A, B, A times B, or maybe A times B, but C also, we can say that they are our terms. Now, let U of X generated by X also, and we want to show that what is universal mapping property. We say that there is two homomorphism as alpha and beta, and we say that alpha goes to, alpha says that X to A, and beta says U of X to A. And if we say that, or maybe if we draw like that, there is alpha, and also there is U of this to A, it's beta, and we say that there is also P. And if we create that homomorphism, we say that it's a universal network property, and if we find that kind of U of X, we say that there is also a free algebra. And a free algebra on a set X is the most general algebra generated by X with no identities given except given ones by that algebraic structure. And also we say that every algebra is a quotidian of some free algebra, and we can see it because of that. And with free algebras, we can say that if we want to understand the behaviors of the algebraic structure, it's enough for us to examine the free algebras and their behaviors with the identities. Also, we use free algebras while making the proof of Birkhoff variety theorem. But firstly, we have to check the theorems about free algebra. Firstly, we say that if there is a sufficiently large X, we can say that A element of homomorphic image of K free algebras of X. Then we say that if K is closed under isomorphism, direct product, and subalgebra, we can say that it's a free algebra element of K also. Now we have to define identities and equation class, but I forgot to mention one thing, and it's very important. Varieties gives us a semantic description. Now sigma, let's sigma denoted by the set of identities, and if we say that for the elements of the class of algebra K satisfy also that identities, we say that K also satisfies sigma. And we say that if every algebra satisfy that identities in sigma, we can say that we can denote it like M of sigma also. And what is identities? For example, we can think about commutative law. For example, if P is equal to X times Y and Q equal to Y times X, then we say that if P equal to Q, we say that that's equality or identity is commutative relations. Also, if K equal to M of sigma, we say that K is an equational class and it gives also syntax definition. Now we will check some theorems about them because we have to make a proof about Birkhoff theorem and they are very essential. Firstly, we say that K and isomorphism class of K, homomorphism class of K, direct product class of K, and subalgebras of K and variety of K satisfy the same identity set. And we say that if K satisfy some identities, then K-free algebras also satisfy that same identities. But we will not use that parts today's presentation, so I skip that. And lastly, Theorem 5 says that if there is an infinite set of variable y, we can say that identity of K of X equal to identity of K-free algebras of Y of X. And if you are interested in them, their proofs are in my report. Maybe we can check them later. Then, almost lastly, we will make a proof of one of our most important lemmas. And lemma says that if Y is a variety and X is a infinite set of varieties, Y equal to M of identity Y of X, we will create a proof because it's most important for the Birkhoff's variety theorem. Now, first, we suppose that V prim equal to M of identity V of X, and we want to show that V prim equal to V. Firstly, we say that V prim contains V because by definition, we know that identity V of X means that if we satisfy P equal Q, then P equal Q element of identity V of X, and because M identity V of X means that all the algebras satisfy that equality, then what we also define V prim is like that. So we say that V prim in fact satisfy that identity also. So V prim contains V, and we do the same thing while find identity V prim X equal to identity V of X also. And by theorem form, we say that if V prim satisfy P equal Q, then its free algebra also must satisfy the same identities. And we also do the same thing for the V. And we saw that the free algebras also equal to each other. But now we change the set and we say that we should choose a suitable infinite set of variables for. And by theorem 5, we say that identity V prim of Y equal to identity V of Y. Even though this equality looks very easy to understand, actually it's very complicated and its proof also long, very long. And we say that by theorem 4, again, the free algebras also equal to each other. Now we choose A element of V prim for that suitable Y, and we say that A element of homomorphic image of that free algebra, but we already showed that free algebras of Y equal to each other under V prim and V, so we replace them here. And we can see that A element of homomorphic class of V free algebras of Y. Then by theorem 2, we already know that V free algebras element of V. So we can say that homomorphic image of that free algebra is also element of V because we know that there is a variety and varieties are closed under homomorphic image. So it's actually very evident to see. And like that, we saw that A element of V. Now we found also V also contains Vpririm, and because Vpririm contains V and V contains Vpririm, and we can finally say that they are egal to each other. Lastly, we will check Birkhoff's variety theorem. It says that K is an equation class and only K is a variety. Its proof is very short because we already showed everything before. First, we assume that K is an equation class. Let's remember what that means. It means that K equal to M of sigma by definition. So we know that V of K and K satisfy the same set of identities. So it means that V of K also satisfies sigma because we say that K satisfies M of sigma there. So we can see that M of sigma contains V of K, but we know that V of K generated by K, so V of K contains K, so they are equal to each other. So K is a variety. That part says that. Now let's suppose that K is a variety. By lemma, then lemma, we are split up. By lemma, we can say that for an infinite set of variables x, K equal to M of identity K of x. So we just replace identity K of x with sigma because identity K of x and sigma like similar kind of sets in fact. Then we just see that K equal to M of sigma, but it's an equational class definition. So we say that yes, Birkhoff's theorem is true, correct. And with Birkhoff's theorem, we can say that there is a connection between a semantic description and syntax description. Also, with Birkhoff's theorem, it gives us a complete characterization of algebraic structures with identities. But also, I forgot to mention one thing. Why we choose a suitable Y? Because Y is also an infinite set of variables and X also an infinite set of variables. So why we didn't use X? Because we can't know that it is, even though X is infinite, we can't know that it's enough for that A. So we have to find a suitable set. So it's the reason why we choose Y. But after all, it's the end of the presentation.
Staging. Hello and welcome everyone. Before we start, I want to say something. I didn't have that much time for this presentation. I actually had 1 week. And I'm having a bit trouble with speaking English part. But if I make any mistakes, I'm sorry. Okay, let's start. My presentation will be about classification of Coxeter groups. We will follow this outline. First, we will start with a brief introduction into Coxeter groups. We will mention what are they, and we will do mathematical definition of Coxeter groups, and then we will follow with the diagrams we used for classification, and then we will dive into classification, finish with conclusion and one last example. Okay, so what are Coxeter groups? Coxeter groups are actually reflection groups. That means each generator are reflections. That means our generators has degree 2 of the group. They often represent symmetries of geometric spaces for many things. As I said before, our generators are reflections, and group structure comes from the relations between them. The diagrams we use for the classification are also the foundation for the classification of simple algebras, but we don't have that much time, so I'll just mention as formal definition of Coxeter groups. If you have a group with this representation, are generators, they are involutions. That means their inverses are themselves, and the relations between them, their product's degree gives us the relation. If it's not finite, there is no relation between two generators. That means we call the generators reflections again. I wanted to give a basic example. Actually, we all know this group, symmetric group on 3 elements, S3. This is a finite Coxeter group, actually. We can write it as with 2 generators, transpositions in S3. And the relations between 2 generators, M1, 2, is 3. That means their product has degree 3 in a group. And this corresponds to A2 Coxeter group in the classification. We will mention this later too. The diagrams we use for classification. A Coxeter diagram is a graph, actually, that corresponds to irreducible Coxeter graphs or Coxeter graphs, Coxeter groups in generally. And a Dinkin diagram is a special type of Coxeter groups, Coxeter diagrams, but they are special because they are satisfying named by Cryprography condition. That means the relation between each 2 generator, must be in this set 2, 3, 4, 6. Only Dinkin diagrams are directly related to classification of simple algebras, so they are important for us normally. But the Cryprography condition established the relation and corresponds to simple algebras. Okay, how can we draw the graph from the presentation of group? We have generators. We are drawing a vertex for each generator, and the relation between 2 generators gives us an information about the graph. If the relation is greater than or equal to 3, we are drawing an H between them. Actually, I can between them, and if the relation and Ij is 3, we are usually not writing the degree, but if it's greater than 3, we are using labeled graphs. We are writing the degree on the H. If it's 2, we are not drawing anything, no H between 2 generators. We will see this on the first example. We mentioned this group before, S3. It has the presentation like this, 2 generators. The relation between them is M1, 2 is 3. That means we have 2 vertices. They correspond to each generators and H between them, but we are not writing 3 in here usually, but if you want, you can write it. There's an H between them. That's it. Actually, I want to give another example for this construction. We have a group like this with 3 generators. They are involutions again. And the relation between generators is given like this. How can we draw its graph? There's a relation between R1 and R2, but the degree is 3, so we are not writing it here. There's a relation between R2 and R3, and it's 4. We are writing it on here. There is no relation between R1 and R3. there is a relation, but it's 2. When it's 2, we are not drawing an H. So this is the graph of the group. This diagram is known as the P3 Coxeter diagram on the classification. Okay, our topic, the classification theorem. A Coxeter group is said to be irreducible if its diagram connected. That means if we have a graph of Coxeter group, its connected components gives us its irreducible factors. Any Coxeter group can be uniquely composed into direct products of irreducible components. We are doing it by looking at its diagram. Okay, first type of irreducible Coxeter groups. These are linking diagrams. Actually, Coxeter diagrams, but the names of these groups coming from their linking diagrams, actually. I call them linking diagrams because they correspond to simple algebras and they satisfy the crystallographic condition. That means Mij is here, 2, 3, 4, or 6. We have classical series and exceptional series, exceptional types. I want to say something in here. Bn and Cn are different Coxeter groups actually, but their deep Coxeter diagrams are same in here. But we will see affine types, they are different. They have different Coxeter diagrams in affine types. These are also finite Coxeter groups or finite irreducible Coxeter groups. They are part of the classification, but they are not satisfying the crystallographic condition. As you can see, 5. We have 5 degree 5 in here. That means they are not corresponds to any simple algebra. Classification theorem for finite Coxeter groups. Every finite Coxeter group is the direct product of finitely many irreducible finite Coxeter groups. We classify these groups by their diagrams again. Okay, we have a table in here for finite irreducible Coxeter groups. As you can see, there corresponds to symmetric groups of some things, some spaces. These are not satisfy the crystallographic conditions, so they are not corresponding to any simple algebra, but the other ones are like this. You want to look. So, okay, the second type of Coxeter groups, there's the Coxeter groups, affine Coxeter groups. They are infinitely, they have infinitely many elements. Like the finite types, they are actually have been completely classified with their diagrams. Their diagrams are extensions of finite types. We are just getting one more vertex of them. They are closely related to affine algebras and describe the symmetries of regular tessellations of Euclidean space like honeycomb or aldırım taşıması diyebilirim. Olabilir. Döşeme Türkçesi.
Tessellation.
Evet ama örnek verirken şey yapalım. Honeycomb dışında bir şeyler. Honeycomb'u anlamışlar. Okay. We have classical series and exceptional types in here too. As you can see, Bn and Cn has different diagrams in here. And last type of Coxeter groups are hyperbolic Coxeter groups. Hyperbolic Coxeter groups are also has infinitely many elements. While affine groups describe the symmetries of Euclidean spaces, these groups are describe the symmetries of hyperbolic spaces. Classification of these groups are far more complex than other ones, so I couldn't add all of them in here, but I want to illustrate it. These are just a few examples. They have names for any names. I should add a lot of things. So just this is 533 hyperbolic Coxeter group, but we can test this part. And the final remarks final remarks. If we have a group, Coxeter group, we can uniquely decompose it into its irreducible components by following this diagram. We are looking at the diagram, and its connected components gives us irreducible factors of group, and that means we have a decomposition like this, and each Wi falls into one of these groups, finite type, affine type, or hyperbolic types. And I want to give an example of reducible Coxeter group. Actually, I made this group up, just made it up. We have 6 generators, and the relation between them is given like this. If you want to look, there's relations between R1, R2, and R3 like this, and R4, R5, and R6 are related and the other degrees are 2. That means we are not drawing anything. So if you look the graph, whole graph, you can see this is one of the connected component of graph. The other one is this, and this corresponds to finite Coxeter group A3, and this corresponds to affine Coxeter group, affine irreducible Coxeter group A2 tilde. That means we can express W like their cross product. That's it actually. Here's my references, and thank you for your attention.
I would like to talk about supervised learning. So what's supervised learning? Supervised learning is defined as when a model gets trained on a labeled data. So what's the labeled data? Labeled data have both inputs and outputs. And depends on your output. It could be classification or regression. There's 2 types of supervised learning. If your output follows categories, it would be classification. If continuous, would be regression. And what's the supervised, unsupervised learning? Unlike supervised learning, unsupervised learning has had not any output, and unsupervised learning finding patterns and relationship without any prior knowledge. And okay, now we can talk about neural networks. What's the neural network? Neural networks is a machine learning model. It's inspired from human brains and composed of interconnected units called neurons or perceptrons. So what's the perceptrons? Perceptrons is inspired from neurons, and its main function is left to signal pass or not. And how it works, as you can see from this mathematical expression, we have a Z. This Z includes W's and X's. X is our inputs and W is our input weights. And we multiplied each of them, and then sum all of these multiplication and get our Z. But to get the complete mathematical description, we have to add the B, which is called bias. Bias is a systematic error. For example, I can explain bias such as when we take a photo, because of the environment, we have some dust, and that's the analogy of bias. And here you can see X's and W's. Again, we, as I said before, we multiplied each X with that weighted, and we sum all of this multiplication and get our Z, actually at our bias 2, and we send this Z into our activation function, and this old process called perceptron algorithm, actually. I would like to talk about some of the activation functions. So what's the activation function? Activation function is a gate that decides the signal should be passed or not. And as you can see from here, that's a step function. It's simplest activation function. And we have the other kinds of sigmoid, ReLU, and TempH. That's sigmoid functions mathematical formula, and it's the graph of sigmoid. And this one is for tonnage and graph of tonnage. And this one is the graph of ReLU. And well, we talked about we have our inputs and multiply these inputs with weights and send these Z into the activation function. And we repeat this process until get our output. This all processes, with this all process on the other layers, and this called feed-forward neural networks. Feed-forward neural networks consist of forward propagation and backward propagation. What's the forward propagation? Same things. We have our inputs, weights, multiply, and sum all of this multiplication, pass it into the activation function, do it and get your output, and your error will be your predicted output, the differences between your predicted output and actual output. That's called forward propagation. So what's the back propagation? Back propagation is used to update the network's weight based on the error between actual and predicted error. So we use error from the forward propagation. As you can see from the figure, error differences between the actual and the predicted ones. And error is sent back to the neurons in backward direction. And gradient of error is calculated with respect to actual each weight, So how it works, we have to adjust our weights for back propagation. We need to gradient our loss function, and then we multiply this learning rate. You can adjust your learning rate, and then we subtract this from our parameters, all parameters. I mean by parameters, weight and biases, and we get our new parameters. Then we use these parameters into our forward propagation. There is a cycle. You have your error here, use this error and take your gradient descent and find your new weights and use into the forward propagation. So we use chain rule. What's the chain rule in here? Because neural network have lots of the layers, there is a composed of the functions. So we have to use a chain rule in it. And okay, at the beginning of my speech, I said we have audio and we transform this audio into the spectrograms, and how the mass spectrograms computed by the LibreSA. LibreSA is a library of Python, and it's derived from the short time Fourier transform. And CNN, we use this model in our project. CNN is a convolutional neural networks. It's is a special type of neural network that's used for images, for audio spectrograms, etc. And CNN composed of the following layers: input layers, convolutional layers, activation layers, pooling layers, flattening layers, and fully connected layers. Now I explain each of the layers. What's the input layers? In a CNN, our input in a tensor with shape, as you can see here, number of inputs, input height, input width, and input channels. What's the meaning of number of inputs? It represents how many samples you have. And input heights represents number of rows, inputs width represents number of columns, and input channels the number of columns for width, input channels number of the colors. Okay, we have our input, and we have a kernel that's called kernel, and it's decided from designer, and we have a dot product in between our input and kernel. Maybe you can see from the image. The second one, actually the right one, is our feature map. It's called feature map actually because we do some operation with kernels on our input and get our feature map. Feature map shape is similar again, number of inputs, feature map height, feature map width, and feature map channels again. As I said, kernels, the kernels rows will be 3 to 3 or 5 to 3. That's the size of our kernel could be. And uses filters across the image. We use the filters across the images. And then each filter extracts one type of features, such as for aids and shapes or more abstract objects in deeper layer. Okay, we have our featured map, and we do something on it. We sense this on the activation function. Again, it is the activation layer. The feature map is then passed through the activation layer. We are using the really rectified linear unit, as I said before, actually explained. And here we have an, for example, as you can see from the feature, if it's greater than 0, it's the same, but if it's less than 0, it will be 0. If it's negative, it will be 0. Really just do something on it. And then pooling layer. Well, we have our featured map now, and we want to reduce this size with a pooling layer. Our pooling layer just a matrix that's empty, by the way, and it can be max pooling or average pooling, and you can adjust your pooling size, pooling layer size. And for example, as you can see from the image, for the first left side, it's 124, and for the next side, it's 278. And for average, we are getting the average of each matrices. Okay, fully connected layer. Well, after the pooling layer, we need to plot our matrix. How? Using the fully connected layer. And after this process, we are doing the same thing in the feed-forward neural networks. After several convolution and pooling layers, the result is flattened into a vector. Dense layer combine extract feature to make a decision. We do with the just multiply all of the sizes of our matrices, and then we get again with this using some same operation on this vector, and again get the Z and send this into the activation functions. Same process like neural network, feed-forward neural networks. That's our output layer. That's the all process into the CNN. You can see. And I want to show some of the pictures from our model. First one is our data set. Before I said, we have the birds audio, and it's in the folders. And we transformed these audios into the spectrograms. Maybe you cannot see it pretty well, but in code I show the CNN and the convolutional layers into the code, but I guess you can see it. And conclusion, we convert our bird sounds into the spectrograms, and then we use these spectrograms in the CNN for classify our birds. And then since each spectrogram is labeled with a bird sound, we will be able to analyze subsequent bird sounds as well. And thank you.
Thank you, everyone. First, I'd like to thank my mentor for guiding me. So I'll just start right now. I'm going to talk about group actions. They are going to permute the elements of an abstract set X in a way that respects the structure of the active group G. This presentation, I'll show this allows us to realize groups as the symmetries of some object. This is how groups were originally studied as transformations. The usual group axioms, as we know them, will come later. I show some examples of group actions, some applications to counting problems with project theorem, and finally end with an overview without the proof of the saddle theorems. So here are the definitions of the group actions. Let G be a group with identity E and let X be a set. An action of G on X is a map by from G and X to X such that the following axioms hold. The first axiom is that E should act as expected. You shouldn't do anything to X. And the second axiom is that letting H act on X and then letting G act on that is the same as just multiplying G and H, then acting on X. For ease of writing, we just write phi G comma X as G times X. X axioms 1 and 2 become this, just here to become easier to read. There's an alternative definition as just homomorphism, where G is a group, X is a set. An action of G on X is just a homomorphism between G and the symmetry group of X. Here should be symmetry group of X. There was a typo here. So immediately here's an example. This is the dihedral group of order 4. It's just acting on the simple set of 1, 2, 3, 4 by sending an element toward its respective vertex sent to by performing the symmetry of the figure. So here's some examples. For example, 1 is sent to 2 by this action, and its permutation representation is this. It's just as a permutation cycle. There are just some other examples. This example shows that the set X that G acts on doesn't even need to have any underlying algebraic structure. Here is the example of SO2, the rotational rotation group, the two-dimensional one. You can just let it act on R squared by a left multiplication. It's a simple calculation to follow the group action axioms. SO2 acts on R squared by rotating the coordinate axis. And this, if you think of square matrices in terms of where they send your chosen basis vectors, you are thinking of its action on the coordinate plane. Cayley's theorem. Every group is isomorphic to a subgroup of the permutation group. So just let G act on itself by a left multiplication. Imagine G as a list, and just for any chosen G, multiply every element in that list by G. It permutes the elements of G in a specific way. So the kernel of this action has to be trivial because only E leaves every element unchanged. So just by the first isomorphism theorem, G is isomorphic to the image of phi, which is a subgroup of the SG, a symmetry group of G. Here I just give some definitions. Let G be a group acting on a set or orbits. The orbit of X is just the set of all elements where X could get sent to by any element of G. If Y is in the orbit of X, then their orbits are equal. Otherwise, they are disjoint. So the orbits of X partition it. I'm not going to prove it. There is also the stabilizers that G act on X. The stabilizer of an element X is the set of elements that fix X. Here is just its definition written out, and just note that stabilizer X is a subgroup of G. Immediately we come with our first important theorem, the orbit stabilizer theorem. Let G be a group acting on a set X, that for any X in X, the order of G is equal to the orbit of X times the stabilizer of X. That's the orders. So immediately an example. Let G be a group of the rigid locations of a cube. Let G act on the set of faces of a cube. The orbit of F has 6 elements. The F gets sent to any of the 6 faces. And the stabilizer has 4 elements. Like you can do 4 rotations along the face here. So the stabilizer has 4 elements. So the order of this group is 24. It has 24 elements. So now I start some counting problems. Maybe another proof of the binomial coefficients formula. Maybe you haven't seen it. Let Sn act on the subsets, the power set of this set, like so. Here's the action. It should be clear that how many subsets this can go to corresponds to the number of k elements subsets of this set, plus the size of the orbit is just equal to this. And we have a formula for this by the orbit stabilizer theorem. It's equal to this. Now we just calculate the respective orders. We immediately know the size of the symmetry group of order n. We just need to calculate the stabilizer. So S sub k, the elements that permute 1 through k among themselves, fix it because they'll be equal under set equivalence. It'll stay fixed. And also the elements that permute k plus 1 through n are also that are isomorphic to S sub n minus k, also fixed 1 through k. Hence, the order of the stabilizer is equal to k factorial times n minus k factorial. And immediately the formula pops out. Here's some more counting problems. How many permutations of the Fano plane are there that preserve collinearity? The circle connecting 2, 4, and 6 is also considered a line. So, for example, if this is a line after we permute it, the image of this line has to be the same. They still have to be the same line. 1, 2, and 3 still has to be on the same line. Let G be the group of those vertices, the permutations of the vertices that preserve collinearity, and let it act on the set of the lines of the Fano plane. So the orbit, let's just consider this line 1, 2, 3. The orbit of this line is its size is about 7 because it could get sent to any of the 7 lines. Now next we consider its stabilizer. First, permutations that fix this line that leave it not unchanged is we could permute along this line. For example, switch 1 and 2 and stuff like that. And for any of those permutations, we could also switch 6 and 7 or not, or switch 4 or 5 or not. So that for each of the permutation here, there are 4 more permutations. So the stabilizer is 6 times 4 is equal to 24. So, for example, an example of such a stabilizing permutation is this, like switching sits at 7 and performing this permutation on these. So by the orbit stabilizer theorem, the order of this group is 168. Next, one last counting problem, we introduce a theorem. It's the orbit counting theorem, or Burnside's lemma, if you know it as that. Let G be a group acting on a set X. Let fixed GX be defined as such. And let R denote the number of orbits of X. Then the number of orbits is just the average of the fixed points. The preceding theorem is useful since you might come across situations where you need to count the number of orbits for a combinatorial counting problem. I'll give an example right away. Before I get to that, let me just give another important example. So let's say we have G acting on an abstract set X, and we have a set of functions from X to S. We might think, is there an action on this set as well? And there's naturally an induced action. This is it. And defining it as this will not give a group action. Can you see why? So let's just immediately apply this.
What was S? S of X.
S could be any set, just like X. Suppose G be the group of rotational symmetries of the cube, X be the set of faces, and S be the set red, green, blue. Then the map, this set, just corresponds to the set of colors of a cube. And we have an action by this automatically induced action. The orbit of a color is this, and the colors that are rotational equivalent if they lie in the same orbit. So we just need to count the orbits. So it's just a bunch of computation, but we just apply the formula. The identity fixes the spherical lines, 90-degree face rotations fixes the spherical lines. And read it yourself if you want, real quick. Too much into detail, but at the end, we come up with 57 rotationally distinct columns of a cube. Group actions also tell us information about the group itself. Representation theory studies action of groups on vector spaces, which allows us to use information from linear algebra to study groups. If we know the order of the group, we can glean a fair bit of information about it via some clever actions, which is the subject of Cauchy's theorem and the Silo theorems. This is Cauchy's theorem. Let G be a group if P divides the order of G, then there exists an element in G of order P. And I'll just use this lemma. Let G be a P group acting on X, then the order of X is congruent to the number of fixed points modulo P, where a fixed point X just has stabilizer the entirety of G. So every G fixes X. This proof is attributed to my thing. I'm just going to give the overview of the proof. Instead of considering this equation, let's just consider the more general equation. G sub 1 times G2 times G sub P equals E, where G1, G2 on G. Let X just be the set of P tuples of G, such that this equation holds. Exercise G, order of G to the power P minus 1, since these elements, we can put any elements, but GP is uniquely determined as the inverse of these elements. Since inverses commute, if this tuple is an X, then we know this tuple is also an X. So this motivates a cyclic action of integers modulo P on X. Let it act on X as such. You can see the action here. It's K acting on this tuple. Just add this K to the indexes, where the subscripts are taken modulo P. Then by lemma 1, this is the order of X is congruent to the number of fixed points modulo P. What are the fixed points of the cyclic action? They're precisely the tuples G, G, G, G. They are not changed, however much you cycle through it. So reframed our problem in terms of fixed points. So this is the set of fixed points, modulo P. And since G is a P group, this is congruent to modulo 0. So this set is at least a multiple of P. It's either equal to 0 or a multiple of P, but it can't be 0 because E is a part of this set, obviously. Because E to the power of P is also E. So there are at least P minus 1 other non-trivial elements in this set, which proves Cauchy's theorem. So just summarizing what I did here. What we did is find a suitable action of the set of solutions and rephrased our problem in terms of fixed points of that action, which is a more reasonable request to work with instead of finding a solution to this really general equation for any abstract group. It could be anything. The silo theorems provide a partial converse to Lagrange's theorem that is given a group groups order. What can we say about its structure? Let G be a group of order p to the power k m, whose p doesn't divide m, and just let silo sub p G denote the set of p subgroups of G of maximum order. We call P a subgroup of G, and we call P, which is a subgroup of G, a silo P subgroup if it's in this set. So the first theorem is existence. I'm not going to prove it. I'll just give you an idea of like what action we used. There exists a P subgroup of G for every power of P dividing the order of G. Hence the silo P subgroup is non-empty, and every non-maximal P subgroup of G lies in some silo P subgroup. The full proofs are in Keith's Conrad's expository notes if you want to take a look at these later. So it's just a proof sketch. The idea is they're given a subgroup H of G with order H P to the power I, which construct another subgroup containing H with order P to the power I plus 1. Then starting from the trivial subgroup, we form a chain of subgroups until we reach the biggest subgroup, which we must reach it because G has finite order. The last subgroup in this chain is the silo P subgroup we desire. It's proved by considering the action of this H on its set of crosets, left crosets by G, by left multiplication. Similarly to the proof of Cauchy's theorem, we use information about fixed point of this action to construct the next in the chain. I'm not going to prove it, that's basically how it goes. Silo 2, conjugate C for H prime P, dividing the order of G. The silo P subgroups are conjugate. Just let P and Q be two silo subgroups. It's proved by just letting Q act on G modulo P via left multiplication of the last process. To show there's a fixed point, yet again, we rephrase that problem in terms of fixed points. That always helps. Just come to this conclusion. K is a subset of this, and since K and P are sets of the same size, they're both maximal P subgroups. It implies Q is equal to this. And lastly, just the number of silo P subgroups. Let G be a group of order this. I already said this. Just let N sub P denote the number of P silo subgroups. Then N sub P is congruent to 1 modulo P, and N sub P divides M. We let P act on the silo sub P G by conjugation. The size of this set is clearly N sub P just by our definition. And we just use lemma 1. N sub P is congruent to the number of fixed points modulo P. It should be clear P is a fixed point since P is equal to G, P times G inverse for all G in P. We just need to show it's the only fixed point so that this is equal to 1. And I won't go into the proof. You can look in the notes, but just one last thing. By silo 2, since every silo P subgroup are conjugate, there is only one orbit of this action. And by the orbit stabilizer theorem, it has to be of size NP and sub P, of course. And because of the orbit stabilizer theorem, n sub b has to divide the order of G, and since n sub b does not divide p to the power k, it has to divide m. So that was the overview. That was a demonstration of the like how powerful group actions can be. And thank you for listening.
Thank you. Today I'm going to talk about, like she said, the representation of abstract finite dimensional algebra as a bound-Q algebra. It's an important thing to do in math because like you can have some problems in the algebra structure, but it may be hard to solve it there, or if you want to show something there, but it may be hard. But it may be easier in the bound-Q algebra structure. So we will focusing on the theorem that says for a finite dimensional algebra that can be assumed to be basic and connected, you can find an admissible ideal of its so-called path algebra such that that algebra is isomorphic to constructed bound-Q algebra. But in order to understand the theorem, we need some basic definitions and some properties. So the first definition is an algebra. An algebra has actually a k-vector space in our context. It has another definition normally, but in our context we will say that an algebra is a k-vector space where k is a field compatible with the multiplication of the ring. So since it has a k-vector space structure, we can talk about its dimension. And we will say that an algebra is finite dimensional if the k-vector space structure of A is finite dimensional. And another important definition is the element idempotent. An idempotent in an algebra is an element such that its square is itself. And also, an idempotent will be called central if it commutes with all elements in the algebra A. And if two idempotents give the zero as the product, then they will be called orthogonal. And idempotent is primitive if it cannot be written as a sum of two non-zero orthogonal idempotents. So after these definitions and after some observations, some calculations, we will claim that for a finite dimensional algebra A, we can find its direct sum decomposition where A is now seen as a module structure, A module structure. So the direct sum decomposition consists of the ideals generated by the idempotents here. Indeed, these idempotents will give the one as their sum, and the set of all these idempotents will be called a complete set of primitive orthogonal idempotents of A. So this set is not actually unique, but we will use the idempotents as the set of a complete set of primitive orthogonal idempotents throughout this talk. Okay, so another definition is the QS. The Q may be visualized as a direct graph here, and it formally has two sets, which is one of them is the set of points, and the one of them is the set of arrows. The points can be seen as nodes, actually, and the arrows can be seen as the direct vertices, the no vertices. I forgot the thing in the graph, whatever. So we will say an arrow alpha is from point A to B is in Q1. Okay, so actually we have two maps that we will not use that much. The maps are from the set of arrows to set of points. One of these maps will map an arrow to its source point, which is A in our context, and the other map will map an arrow to its target point, which is B in our context. Okay, so we will say a Q is finite if these two sets are finite, and we will say that also the Q is connected if its underlying graph is connected. So an underlying graph, as you can guess, is a graph that if you forget the directions of the arrows. Okay, so these are the basic definitions, basic properties. And a path in a Q is actually a sequence of arrows consecutive arrows. A path of length L will have L consecutive arrow that satisfy these three properties. For the source of the path, you will have the point, the source of the first arrow, and the target of the path is actually the target of the last arrow. We also need that the point, the source of an arrow is a target of the previous arrow. So it's basically a composition of arrows and can be visualized as here. Okay. Now the set QL will denote the set of all paths of length L. So Q1 was the arrows, and it's indeed the path of length 1. So Q1 is up. If you consider Q0, it was consisting of the points, and if we agree on that any point corresponds to a path of length 0, which we will call the stationary path, then we will say there is a bijection between the set of points, which is Q0, and the set of all paths of length 0. So the definition of a stationary path is here, and we will write, if we need, as a stationary path, epsilon A. Okay. And also, if you have a path having the same point as its source and a target, then it will be called a cycle. And if a cycle has a length 1, then the cycle is called loop. Okay, now we know the structure keyword. It's interesting that we can find an algebra structure using keywords. So for an algebra structure, first we need an underlying K-vector space structure. So we need a basis. Let all of the paths in the keyword L, in the keyword Q, be the basis of that path algebra. So if you have the basis consisting of all of the paths, then indeed you will have a K-vector space structure. But if you need an algebra structure, you need the multiplication. So to define multiplication between two elements of the path algebra, it's actually enough to define a multiplication between the vectors of the basis. So take two vectors from the basis, which means that take two paths from the basis, and try to add them together. If they have the same point as the first path's target and the second path's source, then just compose them and get a new path. But if this is not the case, then you will get the 0 element of that algebra. Under the definition of multiplication, then you will indeed get an algebra structure that we will call KQ, path algebra of the keyword Q. Okay. So if you're okay with that definition, then after defining KQL, KQ1, KQ2, which are defined by the subspace, which has the basis consisting of all paths of length L, 1 or 0 or 2, whatever, you will get a direction decomposition of the path algebra KQ of the K-vector space KQ as here. So also, this is actually a composed property, but just believe me that if you have finite keyword, then the sum of the idempotents, sum of the stationary paths will give you the identity point of the path algebra KQ. And the set of all stationary points, all stationary paths is a indeed complete set of primitive orthogonal idempotents. Realize that this is indeed an idempotent because of the multiplication defined before. Okay. And also we will claim that the path algebra KQ of the keyword Q is connected if the keyword is indeed connected. Okay, under these conditions, now let's give two examples of a path algebra. So we say that a path algebra is coming from a keyword. So that Q be a keyword consisting of a single point and a single path, actually a single loop. So in order to find its path algebra KQ, we need the basis of the K-vector space structure. So we will find all of the paths and find the basis. So one of the paths is the stationary path. epsilon 1. And another path is the path of length 1, alpha itself. And also if you multiply alpha by itself, then you will get a path of length 2. That's why alpha squared is here. And that's also why alpha to L is here. So one can see that the basis is consisting of infinitely many elements. So our path algebra KQ is infinite dimensional here. But for the next example, we have the keyword consisting of 2 points and arrow between them. So you can try to find another path, but you will not find another path. There are actually exactly 3 paths here, which are epsilon 1, epsilon 2, and alpha itself with the multiplication table here. So this path algebra has 3 dimensions. Okay. So for the other definition, we have the arrow ideal. Arrow ideal of the path algebra KQ is the ideal generated by the arrows. So the underlying K vector space of that ideal will not have stationary paths as the basis vectors. So the arrow ideal will be decomposed by KQ1 plus KQ2 plus KQ blah blah blah. And if you multiply 2 ideals by itself, 2 arrow ideals by 2 arrow ideals, then you will at least multiply a path of length 1 by a path of length 1. And by the definition of multiplication, you will get either 0 or a path of length 2. So RQ squared will have the direct subdecomposition starting from KQ2 this time. In particular, RQL will be decomposed starting from KQL. Okay. And after that, maybe you can see that proposition is a corollary. If you have a keyword that is finite, that is connected and also acyclic, then the path algebra will be basically connected, associative, and finite dimensional. And under these conditions, the KQ, the path algebra KQ, will have the arrow ideal RQ as its radical. And of course, the set of all stationary paths will be a complete set of primitive orthogonal idempotencies. Now, but maybe KQ is not finite dimensional if Q is acyclic. Then to deal with finite dimensional algebra, quotient algebra, we need another ideal called the admissible. An admissible ideal is defined as an ideal that is contained in the RQ squared, but also we need an m bigger than 2 or equal to 2, such that that ideal RQ to m will be contained in I. Under these conditions, you will have I as an admissible ideal. And also we will call the quotient algebra KQ over I is a bound Q algebra. Okay. Now we're getting close. These are 2 examples. Like from the definition, if you take Q as acyclic, then of course any ideal I under the RQ squared will be admissible. And also if you have a finite Q, then any RQ to the M will satisfy the definition, so it will be an admissible ideal. So if you also have a Q shown here, and also if you consider the ideal generated by alpha beta minus, I don't know what's that, sigma, then you will get an admissible ideal because it's contained RQ2 obviously, and probably M is equal to 3 works here. RQ3 will be containing that ideal. But if you consider that ideal generated by alpha beta minus lambda, then obviously alpha beta minus lambda is not in the RQ square, then it's not an admissible ideal. Okay. So this is the case actually here. This is important because we at first want an algebra to be isomorphic to bound Q algebra, but we started with a finite dimensional algebra. So the isomorphic structure that we are going to build will be finite dimensional. So again, we want this bound Q algebra to be finite dimensional. So we will say that if you create this at the bound-Q algebra with an admissible ideal, then you will get a finite dimensional algebra. So as a corollary, we will say that if you have a finite connected Q, realize that Q is not assumed to be acyclic here, not acyclic here, yeah, acyclic here. And let RQ be the error ideal and I be an admissible of the path algebra. Then the bound Q algebra, KQ over I, will be a connected finite dimensional algebra with an identity. Its radical will be the error ideal over I, and the set of all idempotent of the KQ over I, which can be written as the stationary paths plus the admissible ideal set, as a complete set of primitive orthogonal idempotents. So, but we said that for an algebra, we will find a bound-Q algebra. So, to find a bound-Q algebra, we need a path algebra. But for a path algebra, we need a Q. So, starting from an algebra A, finite dimensional algebra A, we need to find a Q related to that algebra. So here we're just doing that. If you have a basic connected that can be assumed to be basic and connected finite dimensional K algebra, then you can find the set of complete set of primitive orthogonal idempotents. And if you just match an idempotent to a number, then you get points of the Q, related Q. And also, if you map any basis vector of the K vector space EA times radical of A over radical squared of A times EB to an arrow from the point A to point B, then indeed you will have the corresponding Q. And after you find the Q, you can also find the path algebra, corresponding path algebra. And we will say that the choice of the complete set of primitive orthogonal idempotents will not affect the Q. Okay. Also, I won't say that these all things needs proof, but since we don't have that much time, I will not be able to do that. Okay. So we will say, if A is connected, then the Q is connected. Now, we start from the algebra, but if we start from the Q, then label A as the bound-Q algebra for I to be for I admissible ideal, then you will find that if you try to find the Q A by itself, then you will get the starting Q. This lemma says that. And after that, now we can understand the first term. Let A be a basic connected finite dimensional K algebra. Then, after constructing a path algebra of the Q A and finding an admissible ideal of path algebra I, then you can find an isomorphism between the starting algebra and between the bound Q algebra. And this isomorphism will be called the presentation of A. Okay. So that was my talk. I really want to thank my mentor, Razia, because she really helped me a lot. So thank you.
Hi, everybody. So with my mentor for 2 months, we've been reading about graph and the application of graph theory to political redistricting. So let me show you the roadmap of my presentation. In this presentation, I'm going to show you what political redistricting is and its importance. Then I'm going to jump to the mathematical modeling of it. Then I'm going to give you some background about graph theory and spanning tree, random walks. We're going to talk about Markov chain. Then in order to solve the problem of redistricting, I'm going to present 2 methods that scientists have developed recently. The flip proposal and the Markov chain, Markov proposal. And after that, we are going to compare the 2 methods. So what is political redistricting? Political redistricting is the process of redrawing the boundaries of a region for political reasons, such as elections, congressional elections. But we don't just want to divide any region however we want. We want to divide in such a way that there will be contiguity and population balance. Contiguity is, you see, every district is made up of units. We want the units to be grouped together. If they are together, we can travel in the district without leaving it. That is contiguity. And then the population balance. We want every district to have nearly the same number of people. Well, how do we model the redistricting problem? First of all, consider the following graph. This is the US map. You see that they have made it a redistricting, a congressional redistricting of it. In order for us to make the problem, we define a variable, xij. A is the unit. I told you before that the districts are made up of units. So we define a new unit xij. If the unit E is in the district G, the variable will take the value 1. Otherwise, it takes the value 0. So we are going to work with this decision variable. Now, for those who know about optimization, I'm pretty sure you know that optimization is about defining an objective function and you put some constraints over the objective function. In redistricting problem, we put 2 or more constraints. In the majority of cases, one of the constraints will be that every unit should belong to only one district, mathematically speaking. This is the condition. The second one is the fact that every district must have nearly the same population. So mathematically speaking as well, this is how it is expressed. Now our objective function. There are many objective functions in the redistricting problem, but we are not gonna go deep into it. I just gave an example of it here. The majority of objective function in redistricting are inequalities, which make the problem even more difficult because it is hard to solve manually. It is classified as an NP hard problem, so we cannot do it mathematically. We will use computation methods to do it. And so scientists have come up with new methods. They apply graph theory to the problem. They develop the flip method and the recall method. So before I go into these methods, I will give you some background of what a graph is. And I'm also going to talk about the Markov chains. Now, what is a graph? Graph is a pair of sets VE, where V represents the set of vertices. The vertices are, consider this example, vertices are A, B, C, D, E. And E is the set of pairs of elements of V. So when there is a relationship between 2 vertices, we say there is an edge between A and B. And this is the set of, in this case, we have the set of edges. Pretty basic definition. Now we have one of the most important concepts in graph theory is spanning tree. What is a spanning tree? A spanning tree is a graph that is connected. That means you can go to any vertex from another vertex. It has no cycle. You cannot turn it around. If you quit R to go to B, the only way you can go back to R is by going back the same. You cannot go. There is no cycle inside. And the third condition in a spanning tree is it contains all the vertices of the original graph. So a spanning tree is a graph that contains all the vertices of the original graph. It has no cycle and each is connected. Now we talk about random walk. What is more important here is the Markov chain. The Markov chain is a sequence of variables over a set of states where the probability of going from a state n to another state n plus 1 depends only on the state n. That is what we are going to apply in one of the methods we are going to develop. So why do we use this Markov chain? Markov chain moves step by step. In this solution state, all of you should agree with me that to divide a plan, there are many solutions. You can divide it however you want. So there are many solutions to the problem of redistricting. We cannot identify all of them, but we want a best map. So we use Markov chain to go into that state and sample from it. We don't want the best map, we just want a good map. That is where Markov chain is interesting and important. Now then, we develop. I show you what a dual graph is. In order for us to apply the method that we develop, we need, when you take a country, suppose this is a country, the map of a country, you need to represent the country as a graph. So from this country, we go to a representation of it as a graph. It is called a dual graph. So for every country, there is a way to make a dual graph of it, and that is on that dual graph that we are going to apply the method I'm going to talk about. So one of the methods is the flip method. How does it work? After you've made your dual graph, you identify the boundary units, meaning when I talk about units, it can be cities, villages, counties, or anything. So you first identify the boundary units. The boundaries that are on the units that are on the edges of two districts. So suppose this is one district, the green one also are another district. So you detect those who are you detect the units that are on the boundary, and randomly from that set, you select one unit and you flip it. You select one unit. Let's select this one. Let's select this unit because it is on the boundary units. And then they flip it to the other. They flip it to the next district. That's how flip methods work. But if you flip a unit to another district, you have to make sure that these two conditions hold. If they don't hold, you don't accept the new map that you get. So when you apply the flip methods, if you get a new map, you have to check whether or not these two, the contiguity connection and the population constraint are satisfied. Now, the second idea is the most important methods, the most used or the newest one is the recall method. So instead of just flipping one unit recall method, it flips a whole district. How does it do it? First, it identifies, after you have made your dual graph, the recall method will identify two neighboring districts. They share a border. Two districts that shares a border. And then it merged them together. Those two districts will become one district. And then it's make a spanning tree of it. I talked about spanning tree before. After it makes the spanning tree, it's cut this spanning tree into two, according to the two constraints that we have, the contiguity and the population balance. It splits the spanning tree into two. Here you see that they split into two, and they get a new map made up of two districts. So from these two districts, they get these new districts. That's how the recall methods work. finally, we compare the two of them. And when we compare it openly, we see that Recon is faster because it doesn't just remove one unit, it moves a whole district made up of many units. Flip is, it just changes one unit. So it is really slow. And that is all I have for you today. Thank you very much for listening.
Hello, everyone. I'm from Yeditepe University. Today, we will start from the basics of category theory, and we will try to move on to topological quantum field theories. And here is our outline. We will give some definitions of category theory, morphisms, functors, universal natural transformations, and we will move to TQFTs. Firstly, I would like to give some motivations for category theory. In mathematics, we have structure, and we have structure preserving maths. Since mathematics is a huge area, we have similar but different concepts like algebra, topology, and geometry. We have structure and structure preserving maths like isomorphisms, homomorphisms. They have similar names, but if we look at the full picture, what we will see? We will see category theory. Yes, and we will use the power of abstraction in category theory. Here is a simple example. And today's journey will start from fundamental concepts, and then we will move. I would like to give an example. Imagine you are standing on an island, and there are things that you can, which we call objects, and actually we will call the left side as category and right side as also a category. We have data in the left side, and one of the first things will come to our minds will be, what can I do in this island? If we have some data, some resources, we can transform them to useful things like hammer, pickaxe, or sphere. And if you want to do a sphere, first we can do a hammer, then if we sharpen it, we can get a sphere. In this picture, the left side, this part will be a category C, this part will be a category D. These hammer and sphere will are functors, and the double arrows sharpening will be our natural transformations. Here is a basic illustration of objects and morphisms in a category. We have two ingredients, objects and morphisms. Objects are the collection of things that you want, and morphisms are the relations or arrows between these objects. Morphisms can be anything you want. I will give some examples in a few minutes. Here's the formal definition. A category sequence of objects, morphisms, and for each object, we have identity morphism from object A to A, and we have composition. We can compose our morphisms. We have two restrictions. The composition must be associative, and the identity composition. For full picture, I like giving full pictures. Here we have lots of restrictions and other rules. In metagraph, we just have objects and morphisms. There are no more rules. But if we put some rules like composition, associative, and identity, we get a meta category. And if you put one more condition, which is this one, morphisms between two objects constitute a set. If you put these conditions as well, then we get a category. So here are some known examples of categories. The category of sets, which objects are set, and morphisms of total functions, and groups, topological spaces, whole sets are other known examples. For example, if you have objects as sets, we can also build another category using sets as objects, but morphisms are partial functions, or we can use relations when we get, and then we get a different category. In category, the important thing is morphisms, not objects. And our main role is cobordisms. Cobordisms
takes n-1 dimensional manifolds as objects, and morphisms are n-dimensional manifolds. For example, if you consider COB1, we can write something like this. 3, 4, 5, 1, 2, 3. And we can now need to draw one-dimensional manifolds, which are lines. You call this part as 5, and the upper part is 3. This is two objects, 5, 3, and the morphisms between 5 and 3. And some less obvious categories, posets, and we can think any money or group as a category if you put some restrictions on our category. And yes, let's take some intuition from the math we already know. In sets, there are some special functions like injective, surjective, and bijective functions. How we can make these ideas more abstract, more general? How can we do it in category? We can define monic and epic. Monic is a morphism from B to A, which is left cancelable, and epic is a map, or it's not actually a map, it's a morphism, which is right cancelable. And in the category sets with total functions, monics and epics correspond to injective and surjective functions, but monics and epics are more general than injective and surjective functions. Here's a surprise. The embedding Z to Q is epic, but not surjective. And for full picture, I give two more definitions: split monic, section, or split epic. For morphisms R and S, if it satisfies this relation, then we call R as a retraction and S is a section. Also, each split monic is a monic and each split epic is an epic. And the gold standard, we all heard, isomorphisms. And if you look at the definition of isomorphism, we can see this G is retraction, F is section, and same thing applies here. If two objects are isomorphic, we call them isomorphic if we find these maps. And yes, we come to known part. In set category, our isomorphisms are bijective functions. In vector category, vector space over K, invertible linear transformations. And like I said, I like giving full pictures. If you consider isomorphisms, we can embed isomorphisms in split monic, bimorphism, and split epic. You may ask, what is a bimorphism? Bimorphism is a morphism which is monic and split at the same time. And of course, we can all embed them into arrows, morphisms. I call arrows morphism, they are same thing. I use them interchangeably. Yes, now we have defined what a morphism is. We have an idea, and we define some different categories. Then how we can relate them, what's the relation between these categories? Like the concrete example, how does the category of groups relate to set? If you take the group and map it to its underlying set G, and take our homomorphisms or isomorphisms as just functions but not homomorphisms, then we get the category set. We will call this U map or U morphisms as functor. Functor is a morphism between two different or same categories. It actually has two morphisms in itself, object mapping and morphism mapping. It maps all elements of C to D and all morphisms of C to D. There are two restrictions on our functors. Functors must preserve identity and preserve composition. Here's a bit of notation. We can do this like this because there are contravariant functors as well. So this could be like this, f of f, composition f of g. This composition might be a bit different than the original one. Yeah, key examples, like we said, forgetful functor and the power set functor, which takes the set from the set category and maps it to its power sets, its subsets. Yes, and we come to universal properties, products. We won't mention other ones like limit, colimit, equalizer, because we won't use them in QFTs. In set, we have Cartesian product or disjoint union. What is the property of this product? It has element from A and B, and it depends on the elements. But in categories, we don't like to just look at elements. We are interested in morphisms. So we define the product of objects in a category. If you have a product candidate, two different product candidates, which can be decomposed in the underlying set with projection maps. If two of them has this property, then there is a unique map from A times B to A times B bar. A times B is not the product, or A times B bar is not the product, because they are isomorphic to each other. Saying this one or this one is product is not meaningful in this content. And this H map needs to satisfy these relations. This triangle and this triangle must commute. And yes, we come to natural transformations. In the linear algebra courses, we saw that V is natural isomorphic to V star star. How can we generalize this idea in categories? We define natural transformations. Natural transformations are the morphisms between functors. We start with morphisms, then we come to functors, then we come to natural transformations. You can think it as dimensions. Morphisms may be considered as dimension 0, functors dimension 1, natural transformations dimension 2, maps between maps, arrows between arrows, functors or the arrows between objects. Natural transformations are the arrows between functors. And in the preceding part, there was something else which I don't remember. But functors, like natural transformations, are the arrows between functors, which needs to satisfy these conditions. And the important restriction on natural transformations is this: we need to satisfy naturality condition. Yes, these are known examples of natural transformations. Maybe the most known is determinant. Like I said, in 0 dimension, we use morphisms. In 1, we use functors. Then we use natural transformations. And this construction leads to higher category theory. We can go on forever, but this is a forbidden place for us. We won't enter that part. And here's the main definition of TQFTs. We define what a monoidal category is. Monoidal category is a category with a bifunctor on it, with a unit and 3 natural transformations. We didn't define what a bifunctor is, but I think it's understandable from the context. And the unit object will be defined soon. We have coherence condition, pentagon and triangle identities. I will show them in a minute. These 3 examples are the monoidal categories, the vector spaces or a field K. If we take this product as tensor product or K, and our identity is the base field K again. Additional structures and additional restrictions on monoidal categories. We will be interested in the symmetric one. Here's the pentagon identity and the triangle identity. And we come to TQFTs. Why would someone study TQFT? Because like Edwin always say, QFT is not rigorous in math and likenesses are huge. So if we define a mathematical perspective for QFTs, it will be pretty useful. We define already more cobordisms. Like I said, objects are closed-oriented n-1 dimensional manifolds. Morphisms are the n-dimensional manifolds between, this should be manifold, n-dimensional manifolds between these n-1 dimensional manifolds, and composition is gluing these manifolds and modular structure. The product is disjoint union. Yes, and the functor Z from cobordisms to complex vector spaces called TQFT and n-dimensional TQFT depends on the dimension of the cobordisms. Here we say for an n-1 dimension manifold sigma, the Z TQFT assigns a vector space which is a Hilbert space on sigma. Why it's a Hilbert space? In quantum mechanics, our functions live on a Hilbert space which is called L2R, square integral functions over R. And here are some examples. Maybe we can write this. These two are n-1 dimensional manifolds. In there, showing this part is in, and this part is out. And the n-dimensional manifold is the connecting manifold, these three circles. Here we can see clearly, I think. And yeah, here's an example. Their product leads to 2 or 1. The TQFTs have applications in string theory and knot invariants, and also 2D TQFTs are isomorphic to commutative Frobenius algebras. Yes, here are my references, and thank you.
About suppose the system starts in state 0. What is the probability that it will be in state 0 at some large time? Long-term probability of being in state 0, starting from 0. We can calculate this by using stationary distribution found. We create for the class T01. We create a system and then solve this system and found that P1 and P0 are our unknowns that we calculate from our system. The answer for this question is, if the system starts in state 0, the long-term probability of being in state 0 is equal to 3/8 or equal to 0.375. The third topics talk about stochastic process in real life. Before we say about when we can see stochastic process in real life, we need to know what means a stochastic process. A stochastic process is a random process that involves with time. In real life, we can see it in finance, stock prices, interest rates, weather, rain, temperature, wind, queues, waiting lines in stores, call centers, traffic, health, disease spread, patients' arrivals in hospitals, in biology, neuron firing, molecule movement, and sports, game outcomes, player performance. I give another example about this. Stochastic process in real life, a weather model. Suppose the weather can be either sunny or rainy from past date. If today is sunny, then tomorrow is sunny with probability 0.8 and rainy with probability 0.2. Also, if today is rainy, then tomorrow is sunny with probability 0.5 and rainy with probability 0.5. We can create a transition matrix with this data, where the first column and row corresponds to sunny and the second to rainy. The question is, if today is sunny, what is the probability that it will be rainy 2 days from now? We can find this by calculate the power of matrix on power 2 by multiply the matrix 2 times. If the day is sunny, the distribution 2 days ahead is given by the first row of P on power 2. So the probability to be rainy in 2 days is 0.26 or 26%. The fourth topic talks about gambler's ruin problem. At first, I presented mathematical formulas, but to make it more clear, I will now explain an example about this. Gambler's ruin problem. Suppose a gambler starts with $10 and wants to reach $100 before going broke, reaching zero in each round. With probability P, the gambler wins $1. With probability 1 minus P, the gambler loses $1. Probability of reaching 100 before zero. Alpha of J be the probability of reaching 100 starting with J dollars, and the formula is given as below. Case 1, a fair game. Suppose that probability is equal to 1 over 2. Alpha of 10 is equal to 0.1 or 10%. So the probability of success is 10%. Case 2, winning advantage. Suppose that probability is equal to 0.6. The alpha of 10 is equal to 0.9827 or 80-90.3%. So the probability of success is about 8.3%. The case 3, losing disadvantage. Suppose that the probability is equal to 0.4. The alpha of 10 is equal to 0. Because since 1.5 on power 10 is extremely large. So the probability of success when the probability that we give is 0.4 is almost 0%. So winning probability of P. When we give a probability equal to 0.5, chance of reaching 100 from 10 is 10%. And when we give a probability that is greater than 0.5, the chance of reaching 100 from 10 is almost 100%, or as on our example is 98.3%. And when we take a probability that is lesser than 0.5, chance of reaching 100 from 10 is almost 0%. These are the reference, and I want to thank you for your attention.
My name is İlhan Deniz Komaracıoğlu. I'm a rising senior in the Department of Mathematics at Middle East Technical University. My advisor is Mahmut Levent Doğan, and we studied representation theory of finite groups. So what is representation theory? It connects two different realms of mathematics, algebra and linear algebra. And it allows us to study abstract algebraic structures, like groups, for example, through their actions on vector spaces. So it adds a computational and concrete flavor to the topic. It reduces abstract algebraic problems to problems in linear algebra, which is a very well understood, very well behaved topic. In this talk, we will study representations of finite groups. Here are my contents. So let's start with the fundamentals. A representation of a group G is a vector space together with a group homomorphism from G into the linear automorphisms of V. So every element in G corresponds to a linear automorphism, which can also be represented by a matrix. Or equivalently, we can think of this as follows. We have a vector space and we have a group action of G on V, so that every element in G induces a linear map. So it acts through linear maps. Okay, I will mention some fundamental notions. A subrepresentation is a G invariant subspace. It's a linear subspace, also closed under the action of G. G times W is in W for all G and for all W. Also, we have representation homomorphisms, or also called G-module homomorphism. It's a linear map, but I wanted to preserve the group action as well. I want every G to be pulled out of F, like this. Or equivalently, I want this diagram to commute for every G. And kernel and the image of a G-module homomorphism are subrepresentations. Here are some examples. For any group G, we have a one-dimensional trivial representation. It's one-dimensional. Take the field complex numbers, for example. The underlying space is C, and the action is given by that. I mean, every G acts as identity. It's trivial one. Also, we have the regular representation. We take the free vector space with basis G. When I use this notation, this set has a representative for every element G. We construct a free vector space with this basis, and I define the formula with this. Define the action with this formula. H times EG is EH. And I extend it linearly. For a symmetric group Sn, we have one-dimensional alternating representation. So every permutation multiplies the vectors by its signature. If it's even, this is 1. If it's odd, this is -1. And also we have the standard representation for a symmetric group Sn. I take all n tuples in Cn such that the sum of the entries is 0. And is given by permuting the coordinates like this. Okay, there are some constructions I want to mention them briefly. The quotient representation, if I have a sub-representation, I can take the quotient space and it becomes a representation with this action. The action of G on a coset is the coset of G times GB. We can talk about direct sum of representations. I define the action to be coordinate-wise. Yeah. Also, I can define tensor product of representations. Just take the linear tensor product, and the action on a pure tensor is defined like this. It's like coordinate-wise. But of course, one should show that this is well defined. You can use the universal property of the tensor product. Also, we can similarly define exterior and symmetric powers. We will take the quotient of the tensor power. This is an important one. The linear vector space of all linear homomorphisms from V into W is a vector space. And if V and W are finite dimensional, there is a canonical isomorphism between these two things. And if we reflect the structure of the second one onto this, but okay, forget about this part. I define the action on. I think I should have mentioned the dual space before that one. Okay, the action of G in an element in the dual space of V, I define it like this: phi composition G inverse. Okay, this is with this action, the dual space of V becomes a representation. Now, V dual times W is V dual tensor W is a representation, and I can reflect this structure onto this one by using this canonical map. Okay, I want to mention complete reducibility. A reducible representation of G is a non-zero representation with no non-zero and proper sub-representation. So we have Maschke's theorem. Let V be a representation of a finite group G over a field K such that the characteristic of K does not divide the order of G. Then for every sub-representation W of V, there exists a complementary sub-representation Y, like this. I mean, I can take any projection pi from V onto W, and I can define this map. This map is a G-module homomorphism, which is also a projection. So it decomposes V like this. And kernel phi is, since this is a G-module homomorphism, kernel of pi is a sub-representation. Then I find the desired sub-representation. So all finite dimensional representations of a group G over a field whose characteristic does not divide the order of G is a direct sum of irreducible representations. Since we are working in a finite dimensional space, if it does not have a sub-representation, then we are done. It's already irreducible. If it has, we can reduce it. There is a sub-representation, and it has a complementary sub-representation. If they are irreducible, we are done. If not, the process goes on. Since we are working in a finite dimensional space, the process must terminate. We can prove it inductively. So we can write every representation as a product of direct sum of irreducible representations. And we have Schu's lemma, a G-module homomorphism between irreducible representations, either zero or an isomorphism. This is a direct consequence of the fact that G-module homomorphisms, the kernel and the image of a G-module homomorphism, are sub-representations. And if V is an irreducible representation of G over an algebraic closed field, any G-module homomorphism from V into V is a scalar multiple of the identity map. This is a little trick here. Let's take a G-module homomorphism. Since the field is algebraically closed, there must be an eigenvalue lambda. Then phi minus lambda I, this is the identity map, is a G-module homomorphism with a non-zero kernel. But the kernel is a sub-representation, so it must be the whole space. So phi must be equal to lambda I. So this can be used to prove that if you decompose a representation into irreducible representations, this decomposition is unique up to the order of the components and up to isomorphism. So they are like irreducible representations are like prime numbers. They uniquely generate every representation if these assumptions hold. If you are working on an algebraically closed field whose characteristic does not divide the order of G. So from now on, all representations are assumed to be finite dimensional and over C, a case in which these assumptions hold. So we can factor every representation uniquely. Here's another corollary of Schu's lemma. If V and W are irreducible representations, the space of all G-module homomorphisms from V onto W has dimension 1 if they're isomorphic and 0 if they are not. So I want to mention character theory now. Character of a representation is a map. It sends every element in G to the trace of the linear transformation induced by that group element. So this is a class function. It is constant on the conjugacy classes in G because the trace is so. So it lives in the space, I denoted like this, the space of all class functions from G into C, which is a vector space whose dimension is the number of conjugacy classes in G. Here's an important theorem. Taking the character of a representation distributes over direct sum like this to tensor over tensor product like this, and the character of a dual representation is the complex conjugate of the representation. This will be important. So for a representation V of a finite group G, I define V superscript G like this. It consists of the vectors in V that are fixed by every group element in G. Also, I define a map like this. This is a Q-equivalent projection, and this is a G-module homomorphism. Now, dimension of VG is the trace of phi, because this is a projection. And if I can distribute trace over this sum, this, by definition, this is the character. Also, note that the space of all G-module homomorphisms from V into W is the same as, not only isomorphic, but it's the same as hom VW superscript G because of that. Because take an element F here, it commutes with every element, so the action fixes F. And converse is also true. Besides, the character of this can be calculated by the previous theorem. Then we proved that this expression here is the dimension of the hom VW superscript G, but this is equals this one, and we already showed this equals 1 if they are isomorphic and 0 if they are not. So this is very important because if I define an inner product, like define a function like this on the Cartesian product of C, the class functions, this is a Hermitian inner product. So we actually proved that characters of the irreducible representations form an orthonormal subset of this space because of this factor. So characters determine the representation. Different representations have different characters. If they have the same characters, they are isomorphic. So we found numerical invariants. And with a little more effort, one can show that the characters of irreducible representations actually form a basis for C class G. Therefore, the number of irreducible representations is exactly the number of conjugacy classes in G. Here you can see a character table. These represent conjugacy classes, because in a symmetric group, conjugacy classes are determined by the cycle types. And these represent how many elements are there in each conjugacy class. These are the irreducible representations of S4, and these are the characters, the traces. This is the trivial one, this is the alternating one, this is the standard one, and this is the tensor product of these two things. I didn't mention this, but even if you don't know what this is, by using relations about characters, you can complete the character table. And by using the character, you can actually construct this W. So this is a powerful approach, I think. So I also want to briefly mention irreducible representations of symmetric groups. But before doing that, I want to mention the group algebra, CG. The CG is the free vector space with basis G, equipped with a multiplication defined by EG times EH equals EGH, and we extend it by linear. So with this multiplication, CG becomes an associative algebra with unity. And if you have a representation of a group, you can extend this linearly to get a ring homomorphism. So V becomes, the representation V becomes a left CG module. Conversely, you can restrict the action, if given a CG module, left CG module, you can restrict the action of CG on that module to get a group representation. Of course, every CG module is also a vector space over C because you can embed C into CG. So we get a group representation. And these are actually equivalent categories. I mean, it's a matter of taste which language you choose. You can express everything in terms of group algebra, modules over group algebra CG. So we know that the number of irreducible representations of Sn equals the number of conjugacy classes, which equals the number of partitions of n. So for every partition lambda of n, there is an associated Young diagram. Here's an example for n equals 4. So for example, take this partition. I put 3 squares here and 1 square here. If 2, 2, I get this one. These are called Young diagrams for partitions of 4. And we have Young tableau. A Young tableau is a numbering of the boxes in a Young diagram. Here are the canonical Young tableau. I ordered them from left to right and up to down like this. So for every partition lambda of n, fix a Young tableau T lambda. It doesn't matter which tableau you choose because the resulting representations will be isomorphic. Take the canonical one, for example. And I will define two sets, P and Q. P is the permutation set of all permutations in Sn that preserves the rows in T lambda. And Q is the set of permutations that preserves the column in T lambda. Let A lambda be the sum of elements in P, and B lambda, the summation is in CG here. I can embed the symmetric group into this group algebra, so this summation makes sense. And B lambda is this sum, every element in Q times their signature. Finally, define the Young symmetrizer to be product of A lambda and B lambda. I will use C lambda for notation. Here's the main result. B lambda, let B lambda be the left submodule of CSN generated by C lambda. Or explicitly, this one, the scalar multiples of C lambda. Scalars are in the ring. Then each V lambda is an irreducible representation of Sn. Also, distinct partitions gives distinct representations. So this actually constructs every single irreducible representation of Sn, and we classify them. We know how to construct them. Also, we have the Frobenius formula. It enables us to compute the character of that V lambda we constructed previously. We define a polynomial, and we are looking at a coefficient here. And that coefficient will be the character of V lambda at a given conjugacy class. I'm not sure whether I want to discuss it in detail because of time issues, but I want to mention hook length formula. The hook length is of a box in a Young diagram is the number of boxes directly to the right and below the box. For example, for this one, it's 6 because 1, 2, 3, 4, 5, 6. This is 1. This is 4. You can use Frobenius formula to prove this identity, and you can inductively prove the following formula. Dimension of V lambda equals n factorial over the product of all hook lengths. So this combines the combinatorics to the algebra, and it shows that how representation theory reveals hidden structure in simple things and how it connects very different realms of mathematics. This brings me to the end of my presentation. Thank you for listening.
Thank you. Well, hello everyone. I know it's been a long day with a lot of presentations, so please bear with me for the next 20 minutes. I'm going to talk about interaction of model theory with machine learning. So first of all, I'm going to talk about model theory, and then I'll go over the basics of machine learning. Then we'll talk more about VC dimension, which is a notion from combinatorics that will make the connection between these two topics. And then after we talk about the connection, we'll say an application of it. So first of all, what is model theory? Well, model theory is a branch of mathematical logic that studies the relationship between formal languages and their models. So from the definition, we have two new words, which is language and model. So let's explain them one by one. First of all, a language, an L language, consists of symbols for function, relations, and constants. In these languages, we have a structure which is formed from the domain, and it is formed with the interpretation of symbols from the language L. And in this language L, we have terms, which can be a variable, a constant symbol, or the symbol of applying a function symbol to other terms. Well, now we talked about structures and terms. Well, we need a way to talk about statements in these kind of structures. That's why we use formulas. So formulas are built from equalities between terms and application of relation symbols to terms using logical connectives and quantifiers. So they are built from terms. In these formulas, we have three variables. We call them free variables when they are not bounded by the quantifier. And if we have a formula without free variables, that's what we call a sentence. To make this more clean for you, I've put two examples. So the first one, we have two variables, which is x and y. And as you can see, they are both bounded by a quantifier. That's why the first example is a sentence. Meanwhile, the second example, we also have two variables, but they are not bounded by a quantifier. That's why the second one is not a sentence. Now we talked about the relationship between formulas and terms, how they are built. But now let's talk about the relationship between formulas and structures. So we see that the structure models a formula, and it is with the symbol on the first row. When this formula is true, it's in this structure. We also have the definition of a theory. A set of L sentences is called a theory. So as I said, sentences are formulas without free variables. And in this theory, we also have models of it. So M is called a model of this theory if M satisfies every sentence in the theory. To make this more clear, I've also put an example here. Here we are at the language L ring, which has two functions, two symbols of the functions and two constants. And the structure that we can build here is the Z structure, which satisfies the theory, which is the theory. So we can write down that Z models this theory. We also give the definition of a type. So a type over A is a variable, is a constant set of formulas using parameters from A with a free variable X. So what we're trying to say here is that a type is like a list of things or a description that we can give for an element in a structure, for a potential element in a structure. We're going to use this definition at the end, but I just wanted to let it out here. So after that, we have the map of universe. So here in the map of universe, we have theories, and we use some nice properties to divide them. The reason why we want to divide them is because we want to distinguish well-behaved theories from more complex ones. One of these well-behaved theories is NIP, which is on the left side of the map on the top part. So that is a well-behaved class. That's why we want to talk more about this. But before talking about an IP, we're gonna give the definition of IP. Well, we say that the formula has IP if there is a model and these two sequences in that model, such that when the model satisfies this formula with these elements, if and only if I is an S. So it's like a membership relation on an infinite set. And now, as you may have thought, a formula has an IP if it does not have IP. And a theory is an IP if no formula in it has IP. We're going to stop here for the model theory part, and we're going to jump straight to machine learning, but we'll come back to it again. So the purpose of machine learning is to program computers so we can learn, so they can learn from input available to them. But why can't we do it ourselves as humans? Because they take care of very large and complex data sets, and they are not easy for us to deal with. So let's describe the problem that we have here. So first we have a domain set, which is a set denoted by X, and it is a set of all objects that we want to make predictions about. For example, in our email accounts, well, the email classifies the emails that come to us by saying they are spam or no spam. So in this case, the domain set would be the set of all the emails that come to us. The label set is the set of possible labels denoted by Y. So in our case, the labels would be not spam and spam. And the most important part is training data, which is a finite sequence of pairs, which are random examples taken from the environment. And this is the input that the learner has access to. So the learner does not know anything about the domain set or the label set. It only knows the data from the training data. So what it's trying to do, it's trying to output a prediction rule. And this is a function, which is called a predictor or a hypothesis. And this hypothesis needs to predict new domain points that are given to him. So he gathers data in our example. He gathers data from the emails that are labeled spam or no spam. And this function, he needs to label other emails that come to us. So how is the training data generated? Well, we assume that the objects are generated from the same probability distribution, which is denoted by P, and which the learner does not know anything about it. We also assume that there exists some correct labeling function, and this function is not known to the learner. Actually, that is what the learner wants to go the nearest to, because it is impossible to exactly find it. So how does it happen? In summary, each pair is generated by first sampling a point from the distribution and then labeling by F. So what might happen? When it outputs a hypothesis, well, how do we know if that is a good one or a bad one? That's why you use the true error of the hypothesis, which is the probability to draw a random instance X, which the correct function F and the hypothesis that the learner output give different values to. But because the definition, as you can see, it uses the distribution and the F, both which the learner does not know anything about. That's why we cannot calculate it directly. That's why we use the training error, which is the error that the learner causes over the training samples, and it is denoted by LS of H. So the main purpose of the learner is coming up with a predictor H that minimizes this training error, and that also performs well on the whole domain set. This part, so coming up with a predictor H that minimizes the training error, is called empirical risk minimization, which we'll be mentioning after 2 lines. But overfitting might happen, which is, it happens when a predictor has very high accuracy on the training set, but it does not work well on the new data points that are given to him. And how can we solve this? Well, we apply the rule over a restricted search area. So from the beginning, without knowing the data, it creates a restricted search area, which is a set of predictors, which is called the hypothesis class, denoted by H. And the main reason why we're doing this is because we want to know if this H is learnable or not. But first, let's talk about what is learnability. That's why we talk about path learnability. So roughly said, a hypothesis class is learnable if given enough examples, a learner can output a predictor or a hypothesis that with high probability, it can go near to the correct function that we want. So if we can go over quickly the definition, well, a hypothesis class H is path learnable if there exists a function and H, and the learning algorithm with the following property that for every epsilon and delta, and for every labeling F and for every distribution T. If the realizability assumption holds, then when running an algorithm on M more than MH, identical and independent examples, then the algorithm returns a hypothesis with a high probability, such as 1 minus delta, where the true error is less or equal to epsilon. So I know that we mentioned some new stuff here. That's why I've added the next slide when we give the explanation for every one of them. So the function MH basically is the number of the examples that a learner wants to have for it to be back learnable. The realizability assumption, where we assume that there exists a function and the true error of that function is 0. The idempotent and identically distributed samples, this guarantees us that there are no correlation between samples and that all samples come from the same fixed distribution. And also we have two parameters, which is epsilon and delta. Epsilon assures us or tells us how close we are to the correct function. And delta tells us how confident we are that we are this close to this function. Well, now that we know what learnability is, we want to know what makes a hypothesis class learnable or no. Well, we know for a fact that all finite hypothesis classes are learnable. We also know that infinite hypothesis classes can be learnable. For example, let's have H be the class of threshold functions over the real line. Even though this is infinite, well, it is pack learnable. So we can say that the size of the hypothesis class does not determine if a hypothesis class is learnable or not. But how can we measure it? That's why we use BC dimensions. Before going to the definition of BC dimension, we need to go over these two definitions first. The first one is the restriction of H to C. Well, H is a class of function from X to 0, 1, and C are some points from this X from the data set. Well, from the name restriction of H to C, we can say that it is a restriction. So from functions from X to 0, 1, we have from functions from C to 0, 1. And shattering, hypothesis class H shatters a set C if the restriction of H to C is the set of all functions from C to 0, 1. And now we can talk about BC dimension. Well, the BC dimension of a hypothesis class is the maximal size of a set C that can be shattered by H. If H can shatter sets of arbitrarily large size, we can say that H has infinite BC dimension. And now we come to the fundamental theorem of backlearning, which says that a hypothesis class H is backlearnable if and only if it has BC finite dimensions. So here we can say that we characterized backlearnability by using BC dimension. So here we have a graphic, if we can call that. So we learned that the backlearnability in machine learning has a connection with BC dimension. Let's see when we have the connection in NIP and model theory with BC dimension. So we're going back to model theory. At first, I've put the BC dimension definition, but this time in model theory. And if you can purge down the two definitions, we can see that they are the same. I've also put again the definition of NIP, just to remind you of that one. And now we can talk about characterization of NIP formulas by BC dimension. First, we need to define this set, so as phi of M, which is the set of sets of elements that satisfies a formula, the formula phi. And we can say that the formula has NIP only if this set has BC finite dimensions. So if we can go back again to the graphic, now we know that there is a connection between model theory and machine learning by NIP and backlearnability because they are both characterized by BC dimension. And now we've come to the application part. Well, for the application, I told you that we are going to need the definition of types, which was the list of things that we can say about the potential element in a structure. Here we also have a new thing, which is phi type. Well, what do we mean by that? It's a kind of type that it is created from instances of formulas, of the only formula phi. And now the first definition tells us about when a type can be definable. So a type can be definable if its behavior depends on only one formula. So as you can see, for all B from A, we have that M models this formula if phi is in P. Another definition is uniform definability of types over finite sets. So a formula has UDTFS if there's a type uniformly defining phi types over finite sets. And now using machine learning tools, one can say that the formula has an IP if and only if this formula has UDTFS. So that's an application of the connection between machine learning and model theory. And that sums up my presentation. Thank you a lot for your time.
Hello everyone, today I will be presenting my work on how to ensure a fair share and cost allocation in collaborative DRP. So here is a small, short outline of what we'll walk through together today. First, we'll start with basic routing problem, then we'll move to vehicle routing problem or VRP. Then we'll explore collaborative VRP, and we look at some game theory concepts, and finish with some experimental results. So what is the shortest route for a single driver to visit all locations and come back to the start? So this might sound simple to state, but it's an NP complete problem, which means there is not an algorithm that solves this problem in a linear time. But in real-world logistics, things are even more complex because we have multiple vehicles. Each of them has different time windows and capacities. So time windows and capacities, which makes it hard to control. So here the vehicle routing comes, it's the way the VRP concept comes in. There are two core challenges in vehicle routing. First one is clustering, which is dividing the set of customer locations optimally to the clusters, where each cluster corresponds to a single vehicle. It's an assignment theorem from a combinatorial optimization. And the second one is routing, which is basically planning each vehicle routes optimally through its own cluster, where our total distance is the minimal. So this is basically the travel settlement problem that we talked earlier. So why VRP is this much important? Because small improvements in the VRP can cause to a really big real-life effects, like given as an example, that some sources report that Amazon saves $1.6 billion every year, and also it prevents 1 million tons of CO2 emissions with the help of vehicle routing. And also, it's not only e-commerce significant, it also has real benefits in the field of food industry, medical supply deliveries, and waste collection. And it's not only economic significance that VRP gives us, it also has an interesting mathematical structure, and it's an NP hard problem, which is the hardest NP problem in this NP problem group. So this means that if we solve this problem, we eventually end up solving all NP problems. This is a huge thing to the whole world and to yourself because you will get $1 million and world will save some income. So let's look at some simple, basic two-index mathematical model in BRP. It's called two-index because our decision variable has two indexes. So we have two decision variables, x, I, j, which is a binary variable. It gets 1 when vehicle travels from I to j, and it's 0 otherwise. The other one is ui, which is the amount of customer demand that already covered after visiting I. But this UI isn't for the whole VRP problem. It is specific for each vehicle. So each vehicle has its own UI value. And we have 4 parameters here. Cij is cost or distance from the customer I to customer j. Qi is our demand for customer I. PQ is vehicle capacity, total vehicle capacity, and K is number of vehicles. So our objective is our main goal. So our main goal is to minimize our objective function, which corresponds to the total travel cost. We have flow constraint. This flow constraint ensures that there is only one edge coming to each customer, and there is only one edge going from each customer, which means each customer is visited exactly once. And the depot constraint, together with flow constraint, ensures that all vehicles leaving depot comes back to depot again. And MTZ Sabtur elimination is our main function here that will go into details in the next slide. And binary constraint is basically a decision variable that we talked earlier. So what is a subtour? Subtour is a loop that forms inside the VRP problem, which doesn't include a depot. So it's a problem for us because if we don't have a depot in our route, how we can deliver packages to the customers if we cannot take the packages, in fact. And when the number of customers grow, the probability of our route forming a depot grows exponentially because our edges grows exponentially. So MTC constraint is the most basic one to prevent that situation. Well, it is one of the fastest working ones because it only time complexity is quadratic, but it has its own downsides. Since it's working fast, it gives really low, weak lower bounds. So to understand this equation better, I gave some motivating example to understand how this formula prevents subtours. So let's imagine we have a subtour, small subtour, like here, that goes from customer 3 to 5, from 5 to 4, and comes back to 3. Then according to the formula, since x3, 5 is equal to 1, because there is a route from 3 to 5, 5 to 3, then that Q's get eliminated, and we get inequality like U3 is bigger or equal to U5 plus Q3, and similarly we get other two inequalities as well. So if we sum up them and remove unnecessary values, we get a contradiction that sum of the demands is less than 0, negative, or 0, which is a contradiction because demand can't be 0 or negative. So by this way, we prevent our route to have subtours. Now let's make things more interesting and add a few more companies. Now imagine we have 3 companies, and company A, trucks of the company A are half empty. Company B has more packages than their trucks can hold, and customer locations of the company C is in the neighborhood of company A. So what if they work together? What if they pool their all customer location and create one single optimized plan to reduce total cost and number of miles driven? So this is basically the idea behind collaborative DRP, specifically horizontal collaboration in this example. So collaborative DRP has two types in the sense of collaboration. The first one is horizontal collaboration. In horizontal collaboration, companies are from same supply chain level, which means they're competitors. They're all same type of companies. They share their depots and vehicles, and they serve each other's customer, and they make joint routing plan together. But in vertical collaboration, companies are from different supply chain levels. So one of them can be a supplier, one of them can be retailer. As an example, we can show that supplier coordinates retailers' inventory and routes. So while this collaborations has lots of benefits such as reducing CO2 emissions, reducing cost, giving better vehicle utilization and customer service, they have their downsides as well. The biggest ones are competition issues, trust issues, real-time data sharing can be hard in vertical collaboration, and also keeping data privacy. And another type is centralized and decentralized collaboration. Where in centralized collaborations, there is a single decision maker. It is a central authority which makes the whole routing plan. Then all companies share their data with single authority, central authority. This may reduce privacy concerns, since all the data, the companies doesn't share their data with each other, and it's more global. But in decentralized collaboration, there are multiple decision makers. So each company shares some part of their information with other companies, and they share their data partially. So here we have more privacy concerns. And it also requires negotiation protocol, since each company wants their own benefit. So the biggest challenge in collaboration is the fair profit sharing. So after they collaborated and they reduced their cost, how they will share their values. So they have some kind of money they get. So what if company A contributed more, but company C contributed less? So if they divide it equally, this might cause to some problems in partnership, in next collaborations, and it causes some unstable collaborations. So to ensure that, they have some formulas. But before going to there, let's get to know some game theory concepts. And so it's our setup. So N is our set of players, and S is subset of N. So it is basically subset of companies. N is our grand coalition, where all companies collaborate. But S is when some companies collaborate, not all of them. So CS is cost of optimal solution for coalition S. That when companies in the S collaborate optimally, their total cost will be C. And X is cost allocation vector, so it is the cost for each company. The index is the company number. So we have two axioms. First is efficiency. This formula means that all costs must be allocated. And second is rationality, which means no coalition pays more than its standalone cost. Because if your coalition pays more than your standalone cost, then what's the point of collaborating? You can go and do your work alone, since you get more money in that one. So the core is one of our solution concepts that ensures both efficiency and rationality axioms and gives some interesting geometry in solution space. But we have the better one, which is Shapley value. Shapley value calculated with this formula, it might seem catastrophic, but trust me, it's not when you understand. The first variable in the product is weight of the customer J. So how much impact customer J has in a coalition. And the second one shows marginal contribution of player J, how much it contributed. So basically this value means how much value does each player add on average when they join all collaborations. The Shapley value is the only method of fair cost allocation, which holds 4 fairness axioms. There are more than 4, but other values hold less than 4 axioms. So it is the one that holds the most. So it's an example to make the formula more clear and to make formula and concept more clear. So let's say we have 3 friends. When the friend A eats in a restaurant alone, she will pay $80. When the player friend B eats alone, he will pay $56. And when player C eats alone, he will pay $70. But when player A and B eats together, they will pay $80 again. And similarly, this goes on. And finally, when they all 3 eat together, they will pay $90. So what is this table? In this table, go there. So if they pay in this order, first player A pays its standalone cost $80. Then we move to player AB. Since the coalition of player AB is $80 again, player B will not pay anything. But since ABC is $90, player C will pay $10 more. And this all goes similarly. If we should give another example, player C pays first $70. Then CB is 72, then B should pay 2 more, and A complete hold the value to 90. So we calculate all values similarly, and then we take its average or mean, and we get their Shapley value. So this is basically what Shapley value is. So this is our experimental results. I used OR tools in Python Jupyter Notebook. So in our problem setup, it is a decentralized VRP. They share same depot. Companies share same depot. We have 3 companies, and the customer of each company showed in its own color. The vertices show customer and edge show root. So this is the graph before the collaboration. Now it is the collaboration of company 1 and 3. Well, actually here the graph a bit changed, but the center location is the same. Just it shows the half of the graph in the previous graph. So you can, maybe it can be hard to see, but we will see, we will also make sure with Shapley values at the end that this graphs really improved. So this is our final graph after all companies collaborated. And, and here are our results. So if we consider it's a randomly generated problem with only 3 companies, we get small slight differences. But when we apply this in a real world instance, these results will improve. But even in these instances, we were able to get some improvements. That standalone cost was 59, but after coalition it dropped to 52.1, which is not bad. So, and in the above you can see coalition cost of coalition cost for each coalition. So that's it.